In the quiet stillness of space, beyond the shimmer of stars and the hum of cosmic background radiation, lies a mystery too vast for any single theory to contain. Science, for all its rigorous methods and revolutionary discoveries, is still at its heart a quest for understanding. It's not merely about facts and figures, it's about the shape of the unknown, the shadows on the wall of the cosmic cave. Many of the popular ideas in science quantum mechanics, the theory of relativity, are widely known. They form the pillars of modern understanding. But this journey will not dwell in familiar territory. We are stepping off the map into ideas that challenge even the seasoned scientists. Here, we explore the peripherous place where physics becomes philosophy, where logic bends under the weight of paradox. These are not the theories you'll hear in documentaries or textbooks. They are the obscure, the profound, the ones that linger on the fringe of possibility. Ideas like vacuum, decay, causal set theory, and the information universe. Concepts that whisper of different realities, untestable dimensions, and laws so alien they almost feel spiritual. And yet, in their complexity, they offer glimpses of something greater, of a universe not just as it is, but as it might be. As we embark on this intellectual odyssey, we'll journey not just outward into the cosmos, but inward to the very edges of human thought. Let us begin one idea at a time. Vacuum catastrophe. Imagine a void. Not a mere emptiness like a silent room or a dark night, but an absolute nothing of vacuum. Now imagine that this vacuum, far from being still, seethes with invisible storms. Tiny fluctuations, ephemeral particles, and silent eruptions of energy pervade this emptiness. This is the paradox at the heart of modern physics. The vacuum is not empty. It is alive. In quantum field theory, the vacuum is defined not by the absence of matter, but by the presence of vacuum energia, constant dance of virtual particles that blink into and out of existence. These are not real in the traditional sense, but they influence reality. Like ghosts leaving fingerprints on the cosmos, they affect the behavior of fields, particles, and even the expansion of the universe. This phenomenon leads us to one of the greatest discrepancies in scientific history, the vacuum catastrophe. When physicists calculate the amount of energy present in empty space using quantum mechanics, the result is staggering, a number 120 orders of magnitude larger than what we observe. This is not just a mathematical oversight, it's a chasm so wide that it suggests something profoundly misunderstood about the nature of the universe. To visualize this, think of building a bridge intended to hold a few tons of weight. Now imagine discovering that it should, according to your calculations, support the weight of an entire planet. Either your math is flawed or you've misunderstood the materials entirely. That's the scale of the mismatch between vacuum energy as predicted and as observed. This anomaly is intimately tied to the cosmological constanta term Einstein introduced to stabilize a static universe, only to later call it his greatest blunder. Yet the term returned, this time as a potential explanation for dark energy, the mysterious force accelerating the expansion of the cosmos. In theory, the vacuum energy should correlate with the cosmological constant, but the numbers don't add up. In fact, they scream contradiction. Some physicists speculate that there may be a hidden symmetry in the universe, one we have not yet grasped, that cancels out the vacuum energy. Others look to string theory or quantum gravity for answers, believing the true nature of the vacuum lies beyond our current understanding. But here's the existential punch. If our vacuum energy calculations were accurate, the universe wouldn't be here. Galaxies, stars, planets, they would be ripped apart by the immense repulsive force of the vacuum. That we observe a calm and structured universe means we are missing something critical. It is not just a theoretical puzzle. It is a riddle etched into the very foundation of existence. The vacuum catastrophe is not merely an error, it is a monument to our ignorance. A quiet scream from the mathematics of quantum mechanics, telling us that something fundamental has been overlooked. Perhaps the vacuum, in all its trembling silence, holds secrets not just about space and time, but about the very blueprint of creation. In the end, this paradox reminds us of the fragility of our theories. How even the most brilliant equations can become incomplete when faced with the infinite complexity of reality. The vacuum, once considered void, has become a mirror showing us not emptiness, but the limits of our understanding. Bohmian mechanics. In the deep corridors of quantum theory, where particles dance to the rhythms of probability, there exists an alternative vision, quiet, deterministic, and hauntingly precise. It is known as Bohmian mechanics, and it offers a rare kind of certainty in a field dominated by uncertainty. Standard quantum mechanics paints a surreal picture. Particles have no defined path, existing as clouds of probability until measured. It's a world of wave functions, collapses, and chance reality where things don't truly exist until we look at them. This is the Copenhagen interpretation, widely taught and broadly accepted, but not universally. Enter David Bohm. In the mid-20th century, he proposed a different view on where the universe does not play dice. In his interpretation, particles always have definite positions and velocities. Their strange behavior isn't the result of chance, but of guidance by an invisible hand known as the pilot wave. Imagine a canoe gliding down a river. In standard quantum mechanics, the canoe is smeared across every possible path until someone watches it. In Bohmian mechanics, the canoe is always on a specific trajectory, guided by the invisible current of the river, the pilot wave. This wave, derived from the same wave function used in standard quantum theory, acts as a hidden guide, directing the particle with perfect fidelity. This deterministic worldview is profoundly appealing to those who struggle with the abstract fog of quantum indeterminacy. It suggests that underneath the randomness lies order and architecture of causality we simply haven't seen. The universe, in this view, is not chaotic but veiled, and yet Bohmian mechanics is not widely accepted. Why? Because it adds elements like the pilot wave that cannot be directly observed. Critics argue it's like adding an invisible conductor to an orchestra that already plays beautifully, albeit unpredictably. It complicates the theory without delivering new predictions, but its supporters argue that the clarity it brings is worth the cost. In Bohmian mechanics, the famous measurement problem of quantum physics, why observation causes a particle to collapse into a definite state imply, vanishes. There is no collapse. The particle always has a state. Measurement doesn't change reality. It merely reveals it. This interpretation also upholds a profound sense of realism. The world exists independently of our observation. The moon is there, even if no one looks. This may seem intuitive, even obvious, but in quantum theory, it's a radical statement. Still, Bohmian mechanics is not without its mysteries. The pilot wave must be non-local, meaning it can influence a particle instantly across any distance. This seems to defy relativity, which limits how fast information can travel. And yet, it doesn't violate causality or allow for faster-than-light communication. It's a subtle paradoxal whisper from the universe that space and time may not be what we think. Despite these challenges, Bohmian mechanics has inspired new research in quantum foundations. It offers not just a different set of equations, but a different way of seeing the world, a philosophical and scientific lens that suggests certainty, structure, and determinism in a realm often described as fundamentally unknowable. In the end, Bohmian mechanics may or may not be the final word in quantum theory, but it remains a powerful reminder that multiple truths may exist beneath the surface, that even in a world ruled by uncertainty, there may be hidden paths straight, sure, and quietly guided by waves we have yet to fully understand. Black hole information paradox. Imagine holding a book, its pages filled with knowledge, its ink pressed with meaning. Now, imagine casting it into a black hole. As it crosses the event horizon, it vanishes. But the question remains, does the information vanish too? Is it gone, forever erased from existence? This is the riddle at the heart of one of the most profound puzzles in modern physics, the black hole information paradox. Black holes, once the stuff of science fiction, are now known as real cosmic objects. Born from the collapse of massive stars, they are regions where gravity is so strong that nothing, not even light, can escape. To an outside observer, the black hole reveals nothing about what it consumes. It's as if information simply disappears. But here lies the paradox. Quantum mechanics, the fundamental theory governing the microscopic world, insists that information is never lost. The wave function that describes a particle state evolves in a reversible, deterministic way. No matter what happens, the full information about a system's past must always be recoverable in principle. If black holes destroy information, it breaks this rule tearing at the very fabric of quantum theory. This contradiction was sharpened in the 1970s by Stephen Hawking's groundbreaking discovery. Black holes are not entirely black. They emit radiation now known as Hawking, radiation through quantum effects near the event horizon. Over time, this radiation causes the black hole to shrink and eventually evaporate. But here's the catch. Hawking's calculations suggested that this radiation is purely thermal, carrying no information about the matter that fell in. If true, this means that once the black hole disappears, the information it consumed disappears too. It's as if a chapter of the universe was ripped out and burned, leaving no trace. This would violate the principle of unitarity in quantum mechanics, the idea that probabilities must always sum to 1 and that the universe must always conserve information. Physicists were stunned. Was Hawking wrong? Was quantum mechanics incomplete? Or was there a hidden mechanism preserving information after all? Many ideas have been proposed. One possibility is that information is encoded in the Hawking radiation itself, but in an extraordinarily subtle way, scrambled beyond our current ability to decode. Another bold idea is the holographic principle, proposed by Gerard A.T. Hooft and Leonard Susskind. It suggests that all the information in a three-dimensional region of space can be represented on a two-dimensional surface, like a hologram. In this view, the event horizon of a black hole might contain all the information about what fell in, stored like pixels on a cosmic screen. There are other speculations. Perhaps black holes don't fully evaporate, leaving behind remnants that preserve information. Or maybe space and time themselves behave differently at the quantum level, hinting at a deeper theory that merges gravity with quantum physics. Some of the most recent work on the paradox comes from string theory and the concept of black hole complementarity, a proposal that says information is both reflected at the horizon and passes through it, but never in a way that lets an observer witness both outcomes. This dual narrative, strange as it seems, avoids breaking any known laws of physics. Still, the paradox remains unresolved. It stands like a silent warning. We do not yet fully understand the nature of space, time, and information. The black hole, in all its darkness, reflects our own blindness or inability to peer beyond the veil. Yet in that mystery lies the promise of discovery. Solving the black hole information paradox may one day lead us to a new theory of quantum gravity, one that does not tear between principles, but weaves them together into a seamless tapestry of vision of the universe in which no story, no particle, no bit of information is ever truly lost. Causal set theory. What if the smooth fabric of space and time, the continuous geometry Einstein so elegantly described, is not continuous at all? What if, instead, reality is stitched together from countless, indivisible pieces like grains of sand that collectively form a beach? This is the radical proposition of causal set theory, that space-time is not a fluid continuum, but a discrete, ordered collection of events. To understand this idea, imagine a digital photograph. From a distance, it appears seamless, a complete image, but zoom in far enough, and you'll see pixels-tiny, distinct units of color and position. Causal set theory suggests that the universe itself might be like this. What looks smooth and continuous from our perspective is actually composed of discrete points, each connected not by space, but by cause. In this theory, the fundamental constituents of spacetime are not atoms, strings, or fields but events, and the structure that binds them is causality. Each event in the universe is linked to others not by physical proximity, but by whether it could have influenced or been influenced by them. These links form a Weber-causal set together, not in space, but in time. This perspective is deeply intuitive in some ways. After all, our experience of the world is causal. One thing leads to another. Every effect has a cause. Yet in physics, especially in general relativity, space-time is treated more as a flexible stage on which events happen not as something built from the events themselves. Causal set theory flips this around. It suggests that space-time emerges from the network of causal relationships. Space and time are not the arena, they are the outcome. The universe doesn't evolve in a smooth arc. It ticks forward like a clock, with an unimaginably fine resolution, one event after another, constructing reality from the ground up. This approach offers a fresh path towards solving one of physics' most enduring challenges, unifying general relativity with quantum mechanics. Relativity works beautifully on cosmic scales, treating space-time as continuous. Quantum theory, on the other hand, thrives in the microscopic realm, revealing a world of uncertainty, discreteness, and granularity. Causal set theory offers a bridge. By modeling space-time itself as a discrete quantum object, it sidesteps the infinities that plague conventional attempts at unification. Black hole singularities, Big Bang, initial conditions, these are places where the smooth geometry of relativity breaks down. But if space-time is a causal set, these singularities may dissolve into more fundamental processes. One of the most elegant features of this theory is its simplicity. A causal set is just a set of elements with a partial order. That's it. No complex geometry. No differential equations. Just events and the order in which they influence each other. Yet from this humble structure, the rich tapestry of space-time may emerge. To visualize it, think of dominoes falling in a pattern. Each domino represents an event, and each fall triggers the next. The pattern of causes and effects defines the shape of the outcome. In the same way, the structure of a causal set could define the geometry of the universe not by measuring distances, but by tracking influence. There's also a profound implication for time. In causal set theory, time is not an illusion or a dimension to be bent. It is the fundamental process. The universe is not a four-dimensional block with all events laid out eternally. It is a growing structure, a crystal of causality expanding one event at a time. The past is fixed, the future open, and the present is the act of creation itself. Though still a developing framework, causal set theory offers a compelling vision of reality. A universe where geometry arises from causality, where time is real and fundamental, and where the smallest grain of existence is not a particle, but an event. It asks us to see the cosmos not as a static expanse, but as a living story written one cause at a time. The Riemann hypothesis. Amid the cold logic of mathematics lies a mystery so profound that it bridges the abstract world of numbers with the fabric of the cosmos. It is the Riemann hypothesis, a conjecture that, at first glance, appears to dwell in the realm of prime numbers, but whose implications ripple outward into cryptography, chaos theory, and the very structure of the universe. To understand its importance, we must first consider primes. These are numbers greater than one that can be divided only by themselves, and 1, 2, 3, 5, 7, 11, and so on. They are the indivisible atoms of arithmetic, the raw building blocks from which all other numbers arise. And yet, their distribution is maddeningly irregular. They come in bursts and gaps with no apparent pattern. Or so it seems. The Riemann hypothesis suggests otherwise. It proposes that this apparent randomness conceals a hidden rhythm, a cosmic order waiting to be uncovered. And at the center of this mystery lies a function, a strange, infinite equation known as the Riemann zeta function. This function was first studied by Bernhard Riemann in the 19th century. He extended it into the realm of complex numbers that have both a real and an imaginary component. There, in this strange and shadowy mathematical domain, he discovered that the function has an infinite number of zeros points where its value becomes exactly zero. Some of these are obvious, known as trivial zeros, but others, the non-trivial zeros, are more mysterious. The Riemann hypothesis asserts that all these non-trivial zeros lie on a single line in the complex plane, the critical line where the real part of the complex number is 1/2. This simple statement has profound implications. If true, it means that the primes are not random. After all, they follow a deeper, hidden pattern encoded in the fabric of the zeta function. But this is more than a mathematical curiosity. The distribution of primes underpins the very foundations of encryption. Modern cryptography, which secures everything from bank transactions to state secrets, relies on the difficulty of factoring large numbers into primes. If the Riemann hypothesis were proven truer, falsight could shake the entire structure of digital security. Yet, proving it has eluded the greatest mathematical minds for over 160 years. Despite extensive computational verification, billions of zeros have been found to lie on the critical Lenino one has been able to show with certainty that they all do. The hypothesis remains unproven, a monument to intellectual perseverance. It is one of the Clay Mathematics Institute's 7 Millennium Prize problems, each worth $1 million reward for a solution. But the true prize isn't money, it's the illumination of a truth that could reshape our understanding of mathematics. Some physicists suspect that the Riemann zeta function is more than just a mathematical tool. Its patterns echo phenomena in quantum mechanics and statistical physics. In particular, the distribution of its zeros resembles the energy levels of quantum system shading that perhaps, deep down, the universe itself is governed by the same principles that organize prime numbers. This suggests something extraordinary, that mathematics is not just a language we use to describe reality, but a structure woven into reality itself. The primes may be silent, but their music shapes the world. So the Riemann hypothesis stands as more than a question of number theory. It is a window into the architecture of reality, a doorway into the unseen patterns that pulse beneath the surface of existence. And whether it is proven tomorrow or in another century, its shadow will continue to stretch across the realms of logic, physics, and the very mystery of order and chaos. Non-commutative geometry. In our everyday world, the order in which we do things often doesn't matter. If you walk left and then forward, you end up in the same place as if you walked forward and then left. This idea commutativity is embedded in our intuitions and reflected in the mathematics that describe space and motion. But what if, at the most fundamental level of reality, this rule breaks down? This is the premise of non-commutative geometry, a bold branch of mathematics that challenges our deepest assumptions about space, time, and the very nature of reality. In this framework, the order of operations matters. Space is not smooth and continuous, but fuzzy, twisted, and intrinsically non-commutative. To grasp this, picture a sheet of graph paper-hour conventional geometry. Move 3 units right, then 2 units up. You'll arrive at the same spot if you reverse the order. Now imagine that the graph paper is warped, not just curved like Einstein's spacetime, but fundamentally altered, so that reversing the order leads you to a different location. This is the realm of non-commutative geometry. The concept is rooted in quantum mechanics. At the quantum level, certain pairs of properties like position and momentum do not commute. Measuring one affects the other. This is encapsulated in the Heisenberg uncertainty principle. The more precisely we know a particle's position, the less precisely we know its momentum, and vice versa. Non-commutative geometry builds on this quantum weirdness. It provides a rigorous mathematical language to describe spaces where traditional geometric notions fall apart. Instead of using points and distances, it uses operators' mathematical entities whose sequence affects the outcome. The geometry of such a space is not defined by the positions of objects, but by the algebra of interactions. The field was pioneered by the French mathematician Alain Connes, who envisioned a universe where the fabric of space is non-commutative at the smallest scales. His work suggests that what we perceive as smooth and continuous may, under intense magnification, dissolve into a chaotic tapestry of uncertainty where geometry and algebra become indistinguishable. Why does this matter? Because it may hold the key to one of the biggest puzzles in physics, uniting quantum mechanics with general relativity. General relativity treats space-time as a smooth, continuous manifold warped by mass and energy. Quantum mechanics, by contrast, reveals a jittery world where nothing is smooth or certain. Non-commutative geometry offers a possible bridge. By reformulating the geometry of space-time in non-commutative terms, it allows quantum theory to coexist with gravity. It provides tools to describe quantum space-time, a place where space and time themselves become uncertain, interwoven, and non-commutative. This approach has already found applications in string theory and particle physics. In certain versions of string theory, space-time coordinates do not commute, leading to non-commutative models of the universe. These models suggest that at incredibly small scales near the Planck length space becomes grainy, and time itself may flow differently. There are even hints that non-commutative geometry could illuminate the Big Bang. Traditional physics breaks down at that singularity, unable to describe what came before. But in a non-commutative framework, the singularity might be avoided. The early universe could be understood not as a point, but as a quantum algebraic state from which space and time emerged. Beyond physics, non-commutative geometry is a philosophical revelation. It challenges the notion that reality is fundamentally spatial, reducible to points and paths. Instead, it invites us to think of reality as a relational network of interactions, where what matters is not where things are, but how they influence each other. In this vision, the universe is not a stage upon which particles perform. It is a score of operators, a symphony of sequences. And in the subtle interplay of non-commutative relations, perhaps we will find not just new physics, but a new understanding of existence itself. Twister theory. At the intersection of geometry, light, and imagination lies a theory so radical that it seeks to rewrite the foundations of physics not by building upon the known, but by turning our entire framework inside out. This is twister theory, a mathematical construct introduced by Sir Roger Penrose, which suggests that we've been looking at the universe from the wrong perspective all along. Traditionally, physics locates objects in space-time using coordinates 3 for space, 1 for time. Every particle, every event is plotted somewhere on this 4-dimensional map. This system has served us well, forming the backbone of general relativity and quantum field theory. But Penrose dared to ask, what if these coordinates are not fundamental? What if the basic entities of the universe are not points in space-time, but light rays? Twister theory replaces space-time points with Twister's mathematical objects that encode the paths along which light travels. In this framework, the geometry of space-time emerges not from distances and positions, but from how these light paths intersect and relate. Imagine watching a movie. You see characters move from scene to scene, events unfolding across locations. In space-time physics, you'd study the frame-by-frame positions. Twister theory, in contrast, watches only the beams of light tracing connections between events, stitching the film together not by content, but by continuity. This radically different viewpoint reveals remarkable simplicity in otherwise intractable problems. Complex equations in quantum field theory, especially those involving massless particles like photons or gluons, become far more elegant when translated into twister space. It's like solving a maze by lifting the page and seeing the path from above. More importantly, twister theory provides a fresh angle on the long-standing conflict between general relativity and quantum mechanics. General relativity describes a smooth, continuous space-time shaped by mass and energy. Quantum theory, however, deals with probabilities, uncertainties, and discrete interactions. Their unification has proven elusive. Twister theory sidesteps this clash by shifting the focus from space-time itself to the light-like structures that connect events. In twister space, time and space are not coordinates, but consequent submergent properties of a deeper geometric web. This makes twisters inherently suited for describing quantum processes while remaining compatible with the curvature of space-time. One of the most profound features of twister theory is its elegance. In conventional physics, simplicity is rare. Equations, balloon, interactions tangle, and infinities abound. Twister theory, by contrast, often collapses pages of equations into a few graceful lines. In doing so, it hints that perhaps our traditional models are unnecessarily cumbersome, that the universe, at its core, might be governed by beauty as much as by logic. This isn't just poetics, it's practical. Twister methods have simplified complex calculations in particle physics, especially in the study of scattering amplitudes, where particles collide and exchange energy. In standard space-time, these calculations are daunting. In twister space, they become manageable, even intuitive. Still, twister theory remains on the fringe. While it has gained renewed interest, particularly with the development of newer twister-inspired frameworks like the amplituhedron, it has yet to dethrone the mainstream pillars of theoretical physics. But perhaps that is fitting. Twister theory doesn't seek to dominate the current paradigm, it offers an alternative path, one that flows not from position and velocity, but from connection and continuity. In its heart, twister theory is a philosophical gesture as much as a scientific one. It suggests that the universe may not be built from blocks of matter in a static grid, but from pulses of light in a fluid dance. It reframes existence not as a collection of isolated events, but as a tapestry of luminous threads woven not in space and time, but through them. Fractional dimensions. We are taught from childhood that dimensions come in whole numbers. A line is one-dimensional, a square is two-dimensional, a cube has 3 dimensions, and so on. But what if nature doesn't always follow such tidy rules? What if reality is more complex, more granular, and infinitely more intricate than whole numbers can express? This is the realm of fractional dimension sand idea that reveals a deeper fractal logic underlying the universe. To understand fractional dimensions, consider a coastline. From afar, It appears to be a simple curvy line tracing the border between land and sea. But as you zoom in, detail upon detail emerges. Coves, crags, inlets, and peninsulas. The closer you look, the more complex it becomes. No matter the scale, new patterns appear echoing the shape of the whole. This self-similarity is a hallmark of fractal shapes that look similar no matter how closely you examine them. But here's the strange part. Coastlines, like many natural structures, don't fit neatly into the category of a one-dimensional line or a two-dimensional surface. Their geometry demands something in between. Enter the concept of fractional or fractal dimensions. Unlike the dimensions we're familiar with, these aren't integers. They can be 1.3 or 2.7 numbers that suggest partial occupation of a space. A fractal curve may fill more area than a line, but less than a plane. It's as though it's reaching toward the next dimension without fully inhabiting it. One of the earliest and most iconic examples of a fractal is the Koch snowflake. It begins with a simple triangle. At each step, smaller triangles are added to every side, creating increasingly complex edges. This process continues infinitely, and the perimeter grows endlessly while the area remains finite. The snowflake exists in a fractional dimension, more than one, less than two. This idea is not just mathematical artistry. It has deep implications for science. Fractal dimensions describe the branching of trees, the structure of lungs, the networks of rivers, and the way galaxies cluster in the cosmos. These structures are too complex for classical geometry, yet too ordered for chaos. Fractals are their natural language. Even the human brain exhibits fractal characteristics. The folds of the cerebral cortex increase surface area without increasing volume of fractal efficiency that may be key to higher cognition. The patterns of neural connections too show signs of self-similarity and non-integer dimensionality. Understanding these fractal properties could provide insight into brain function, consciousness, and neurological disorders. In physics, fractals emerge in surprising places. In turbulence, lightning, and quantum mechanics, systems exhibit behavior that resists simple dimensional description. Fractal dimensions offer a way to quantify this complexity, capturing the irregularity that defines the edge of chaos. They also play a crucial role in image compression, computer graphics, and modeling natural environments. Fractal algorithms can generate mountains, clouds, and forests that look astonishingly real. Why? Because nature itself is fractal. By mimicking its geometry, we can simulate its appearance with remarkable fidelity. But perhaps the most profound implication of fractional dimensions is philosophical. They challenge our linear, compartmentalized view of reality. They suggest that between any two certainties lies a realm of complexity, a continuum of form that refuses to be boxed into categories. The universe, it turns out, is not made of clean lines and perfect cubes. It is woven from patterns that repeat and mutate, grow and twist, hover and flicker between dimensions. Fractional dimensions show us that reality is not just bigger or smaller than we imagined. It is stranger. It is textured, recursive, and deeply connected. It reminds us that simplicity is often an illusion, and that beneath the smooth surfaces we trust lies a wilderness of detail infinitely unfolding, dimension by dimension, never quite arriving, but always revealing more. Spin networks. In the quest to understand the universe at its most fundamental level, scientists have begun to unravel a vision of space that is not smooth and continuous, but woven like a cosmic tapestry made from threads of quantum information. These threads are called spin networks, and they may hold the key to one of the greatest challenges in physics, the unification of general relativity and quantum mechanics. Spin networks were first proposed by Roger Penrose as a way to visualize and mathematically represent the structure of space on the smallest scales. At their core, spin networks are graphs collections of nodes connected by links, but these links are not simple lines. They are carriers of quantum information, specifically a property called spin, which is a fundamental attribute of particles. Each node in a spin network represents a quantum of space a tiny, indivisible chunk. The links between nodes describe how these quanta are related, how they spin and influence each other. This network doesn't sit inside space. It is space. There is no background, no coordinate system. The geometry of the universe emerges from the web of relationships encoded in the spin network. This is a profound shift in perspective. In classical physics, space is the arena in which events unfold. It is continuous, stretching infinitely in all directions. But in the world of spin networks, space is not the backdrop. It is dynamic, quantized, and evolving. It arises from the interplay of connections, like a melody emerging from the arrangement of notes. Spin networks form the mathematical foundation of a theory known as loop quantum gravity. This theory attempts to merge Einstein's general relativity with the principles of quantum mechanics. Instead of viewing gravity as a force transmitted through spacetime, loop quantum gravity treats spacetime itself as a quantum objective network of loops, spins, and interactions. In this model, spacetime is granular, with the smallest unit being the Planck, length about 10⁻³ circumflex, 35 10⁻35 meters. At this scale, the familiar concepts of distance and time break down. There are no straight lines or smooth curves. There are only nodes and links whose interrelations determine the geometry and curvature of the space they compose. What makes spin networks so intriguing is that they evolve. The links can stretch, contract, change direction. New nodes can form, old ones can vanish. This dynamic nature allows the geometry of space to shift, bend, and ripple just as it does under the influence of mass and energy in general relativity. But here, the motion is governed by quantum rules. The result is a universe that is not only alive with motion, but fundamentally constructed from change. Imagine watching the universe being built, moment by moment, node by node. The web flickers with activity. Some connections glow brighter, carrying more spin, others dim. The entire network pulses like a breathing organism. This is not an abstract metaphor. In the spin network model, reality is quite literally a quantum web. The implications are enormous. If space is quantized, then singularities like those inside black holes or at the Big Bang may not be true infinities. Instead, they may represent limits where our classical descriptions fail, but the underlying spin network remains intact, offering continuity where the old models break down. Spin networks also hint at a universe where space and time are emergent phenomena, not fundamental ingredients of reality, but consequences of deeper relational structures. In this view, time does not flow in the way we perceive it. Rather, it is the unfolding of connections, the reshaping of the network. The passage of time is the evolution of geometry. In embracing spin networks, we are invited to see space not as an empty void, but as a vibrant lattice of interaction. It is a radical yet compelling vision in which the universe is woven from quantum threads, each a note in a grand, unseen symphony of existence. Emergent space-time. What if space and time, the very framework of our existence, are not fundamental? What if they are not the canvas on which the universe is painted, but rather the painting itself? This radical idea, known as emergent space-time, suggests that space and time arise from more basic ingredients underlying principles of quantum physics that do not themselves require a backdrop. At first, this seems incomprehensible. After all, everything we observe takes place in space, unfolds in time. But throughout the history of physics, what once seemed absolute has often turned out to be emergent. Heat, for example, emerges from the random motion of countless molecules. Solidity arises from electromagnetic interactions between atoms. Perhaps space-time is no different. In this view, the universe at its most fundamental level has no geometry, no clock, no dimensions. Instead, it consists of abstract quantum entity states, entanglements, correlations. From the dense web of these relationships, space-time materializes like a hologram projected from a flat surface. One of the most compelling insights into this idea comes from the holographic principle. It proposes that all the information in a volume of space can be encoded on its boundary like a three-dimensional image encoded on a two-dimensional film. This principle emerged from the study of black holes, where it appears that the entropy or information content of a black hole is proportional not to its volume, but to its surface area. If this is true of black holes, perhaps it is true of the entire universe. Perhaps we are living in a vast cosmic hologram, where space and time are not real in the way we think, but are emergent projections from a deeper informational substrate. This idea gains even more strength from studies in quantum entanglement. When two particles are entangled, their states are linked no matter how far apart they are. Recent work suggests that the very fabric of space may be woven from these entanglements. That is, the more two regions of the universe are entangled, the closer they appear in space-time. Geometry, in this vision, is not fundamental, it is the pattern of entanglement. Theorists like Mark van Ramsdonk have proposed that space-time itself could emerge from quantum entanglement, that the structure of space is a result of how quantum information is shared. This is a seismic shift in our understanding. It replaces the stage with the script, the background with the dialogue. What we perceive as motion, distance, and duration are merely the shadows of a deeper play-on that unfolds not in space and time, but in the pure logic of quantum relationships. Emergent space-time could also solve the greatest paradoxes in physics. General relativity and quantum mechanics describe the universe with stunning accuracy, yet they are fundamentally incompatible. Space-time singularities like those at the heart of black holes or the Big Bang defy both theories. But if space-time is not fundamental, then these singularities may not exist in the foundational layer of reality. They are illusions that vanish when seen from a deeper, pre-geometric view. This is not science fiction. From string theory to loop quantum gravity to tensor networks in condensed matter physics, the idea of emergent space-time is being mathematically explored. Each approach is different, but they all point toward the same conclusion, that space and time may not be primary ingredients, but emergent phenomena built from quantum correlations. Philosophically, this idea is transformative. It suggests that what we consider the most basic aspects of existence where we are, when we are not intrinsic to the universe. They are context-dependent, relational, emergent. We are not floating in space. We are entangled within it, not moving through time, but participating in its unfolding. In this paradigm, the universe is not a place, but a process. Space is the texture of entanglement. Time is the rhythm of change. And behind it all, hidden beyond the veil of perception, lies a more profound truth, that the cosmos is not made of things, but of relationships, and that from these relationships, space-time is born. The information universe. What if the universe isn't built from particles or fields, but from something even more fundamental, information? This is the core idea behind the information universe hypothesis, a radical yet increasingly influential perspective that reframes everything we know about reality. It proposes that matter, energy, space, and even time arise from the processing and relationships of bits of information. To grasp this concept, consider what information really is. At its simplest, information is a distinction, the answer to a question, the resolution of uncertainty. In the digital world, all information reduces to binary code, ones and zeros, yes and no. Now, imagine that everything in the cosmos from quarks to quasars is a manifestation of such binary logic. This idea was famously captured by physicist John Archibald Wheeler in his phrase, "it from bit." He believed that every physical entity, it, is at root a manifestation of informational distinctions, bits. This is not merely poetic. In many physical theories, information is not just a helpful description, it is conserved, quantified, and treated with the same seriousness as mass or energy. In black hole physics, for example, the information paradox forces us to reckon with how data about objects falling into a black hole is preserved. The holographic principle, which emerged from these studies, suggests that all the information within a volume of space can be stored on its surface area, hinting that reality itself is a kind of computational process. Quantum mechanics takes this further. The state of a quantum system encodes information, and that information evolves according to specific rules. When two particles become entangled, their states are linked no matter how far apart they are, a phenomenon that looks less like a mechanical interaction and more like the transmission of information across a hidden network. In this light, the universe resembles a massive quantum computer machine, whose fundamental operations are the interactions of quantum bits, or qubits. These qubits don't sit in space. Rather, space emerges from their interrelations. What we perceive as objects are stable, recurring informational patterns. What we call motion is a change in these patterns. The laws of physics, then, may not be eternal truths, but the rules of a program, a cosmic algorithm, and just like code, they may evolve. Some researchers even suggest that the universe could be self-modifying, rewriting its own rules as it unfolds. This vision of reality has practical consequences. It informs cutting-edge research in quantum computing, where the manipulation of information at the quantum level could unlock unprecedented computational power. It also guides explorations in theoretical physics, as scientists try to recast general relativity and quantum field theory in purely informational terms. But perhaps the deepest implications are philosophical. If everything is information, then the boundary between physical and abstract dissolves. Reality is no longer made of stuff, but of meaning relationships, distinctions, possibilities. The universe is not a machine, but a message. And if we are part of this universe, then so are our thoughts, dreams, and consciousness. These too may be informational structures configurations within the grand computational flow. In this view, understanding the universe becomes not just a matter of particles and equations, but of decoding, interpreting, and engaging with the language of existence itself. Imagine standing on the shore of a vast oceanid of water, but of information. Every wave is a fluctuation of knowledge, every current a link between meanings. The stars above are not distant spheres, but luminous nodes in a cosmic web of data. We are not separate from the sea, are strands within its weave, thoughts within its processing, questions seeking their answers. In such a universe, the fundamental act is not observation, but comprehension, not force, but logic, not mass, but meaning. And in every atom, every photon, every entangled pair, and every coded string, the universe whispers its source, a structure born not of matter, but of mind. Quantum Darwinism. In the tangled intersection of quantum physics and natural selection lies a theory as audacious as it is elegant: quantum Darwinism. It draws inspiration from evolution, yet applies it not to genes or species, but to the very fabric of physical reality. The theory seeks to explain a fundamental mystery. Why does our world, at the macroscopic level, appear classical, definite, and objective, when at the quantum level, reality is strange, uncertain, and fluid? Quantum mechanics tells us that particles exist in superpositions, states where they are in multiple positions, orientations, or conditions simultaneously. An electron can be both here and there, a photon both spinning left and right. But we never observe this strangeness directly. Instead, we see definite outcomes: coins land heads or tails, cats are alive or dead. So where does the classical world come from? This is the quantum measurement problem. The Copenhagen interpretation simply states that the act of measurement collapses the wave function, reducing many possibilities to a single outcome. But this answer is unsatisfying. What exactly qualifies as a measurement? Why does observation seem to dictate reality? Enter quantum Darwinism. Proposed by Wojciech Zurek, this theory offers a more nuanced, naturalistic explanation. It suggests that the classical world emerges through a kind of quantum natural selection. When a quantum system interacts with its environment, say, a particle bouncing off air molecules or photon certain properties get copied and spread, but not all information is equally likely to survive. Only specific features of the system, those that are stable, redundant, and robust, get recorded by the environment in a way that multiple observers can access. These are called pointer states, and they act like the fittest traits in Darwinian evolution. They replicate, persist, and become objective reality, while the rest of the quantum information fades into oblivion. Imagine walking into a forest. You hear leaves rustle, feel the breeze, see light filter through trees. Each of these sensory inputs is a fragment of environmental information. But you don't perceive the quantum states of individual atoms in the trees, you perceive the stable, classical image of a tree. That image is the result of quantum Darwinism. The information about the tree's large-scale properties has survived the interaction with the environment and reached your senses. This mechanism explains why we don't see quantum superpositions in daily life. It's not that they don't exist, but that our environment has filtered and amplified only certain outcomes. Just like evolution favors traits that enhance survival, quantum Darwinism favors states that can be redundantly imprinted into the world around them. These are the states that survive observation by the environment and become the reality we all agree on. It's a profound realization that the classical world is not separate from the quantum, but a filtered version of Ida shadow cast by deeper possibilities. Objective reality, in this view, is the consensus formed by redundant information spread through the environment, accessible to many observers without direct quantum measurement. Quantum Darwinism has implications beyond philosophy. It influences how we think about decoherence, the process by which quantum systems lose their quantum behavior due to environmental interaction. It also informs the design of quantum computers, where preserving superpositions and avoiding decoherence is critical. More broadly, it reshapes our metaphysical assumptions. It tells us that reality is not absolute, but emergent, that what we perceive is not the full story, but the result of a natural process that selects and stabilizes certain quantum features over others. In essence, quantum Darwinism offers a bridge away to walk from the shadowy world of quantum probabilities to the firm ground of classical certainty. It reveals that the universe we see is not the collapse of possibility, but the survival of the fittest information. And perhaps, in that realization, we see a deeper truth, that evolution is not confined to life alone. It is a universal principle shaping not just species, but the very nature of reality itself. Supersolids. Imagine a substance that flows without friction, gliding endlessly like a ghost, yet simultaneously holds its shape like a rigid crystal. It sounds paradoxical and impossible even. Yet, this is the nature of a supersolid, one of the most mind-bending states of matter ever theorized and, more recently, observed in the laboratory. In our familiar world, we categorize matter into solid, liquid, gas, and plasma. Solids resist deformation. Their atoms are locked into structured, repeating lattices. Liquids, on the other hand, flow freely, conforming to the shape of their containers. A substance can be one or the other, but not both. Supersolids defy this division. They possess the ordered structure of a solid and the ability to flow without resistance, like a superfluid. To understand how such a state could exist, we must journey into the quantum realm, where particles behave not as tiny billiard balls, but as waves interfering, overlapping, and entangling with each other. At extremely low temperatures, close to absolute zero, quantum effects begin to dominate. At these temperatures, certain materials enter a superfluid state. They can climb walls, pass through narrow channels without slowing, and continue moving without losing energy. Supersolidity extends this phenomenon into a solid lattice. In a supersolid, some of the particles remain fixed in position, forming the repeating structure of a solid. But others, bizarrely, delocalize coexisting in a quantum state that allows them to flow through the solid without disturbing its lattice. It's as if part of the material remains frozen in place, while the rest becomes a ghostly current, gliding through it. The concept of supersolidity was first proposed in the 1960s, largely as a theoretical curiosity. Helium-4, a well-known superfluid, was considered a likely candidate. If cooled and pressurized correctly, scientists theorized it might exhibit both solid and superfluid characteristics. For decades, the evidence was inconclusive whispers in data, hints in behavior, but nothing definitive. Then, in the early 2000s and again in the 2010s, advances in ultra-cold atomic physics changed the landscape. Using clouds of rubidium atoms trapped in laser-generated optical lattices, researchers managed to engineer conditions that gave rise to clear signatures of supersolid behavior. In these systems, atoms arrange themselves in an ordered grid, like a solid, yet move collectively and frictionlessly, like a superfluid. What's happening at the quantum level is deeply strange. Atoms in a supersolid form a kind of macroscopic wave function a shared quantum state where each particle loses its individual identity. They become part of a collective rhythm, dancing to the same invisible tune. This coherence allows for frictionless flow, even as the underlying structure remains intact. Supersolids challenge our understanding of phase transitions, the conditions under which matter changes from one state to another. They reveal that the boundaries between phases are more porous than we once believed, that new hybrid states can emerge, where the rules blur and quantum strangeness dominates. The implications extend far beyond condensed matter physics. Supersolids offer a window into the interplay between order and motion, between structure and freedom. They suggest that stability and fluidity are not opposites, but can coexist in perfect harmony under the right conditions. In technology, these materials are still in their infancy, but they hold tantalizing promise for quantum computing, precision sensors, and other applications that depend on manipulating quantum states with stability and control. Their dual nature structured yet flowing could unlock new architectures for devices we've yet to imagine. Philosophically, supersolids are a reminder that reality is more flexible than we assume, that the categories we impose, solid, liquid, motion, stillness air, sometimes artificial boundaries. In the quantum world, opposites can merge, paradoxes can become real, and the universe reveals new facets of itself through states we never dreamed possible. The REPR conjecture. There is a whispering thread that ties together the two deepest mysteries in physics, black holes and quantum entanglement. At first glance, these phenomena belong to entirely different worlds. One deals with massive objects warping spacetime. The other describes the strange, interconnected behavior of tiny particles. But a bold conjecture, known as EREPR, suggests that they are not just related, they may be the same thing. The name EREPR comes from two historical touchstones in theoretical physics. ER refers to the Einstein-Rosen bridge, or wormholea theoretical tunnel through spacetime connecting two distant regions. EPR refers to Einstein, Podolsky, and Rosen's 1935 paper on quantum entanglement, which described how two particles could instantaneously affect one another no matter the distance. Einstein famously dismissed this phenomenon as spooky action at a distance. Yet, in 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical unification, that every entangled pair of particles is connected by a microscopic wormhole. ER equals EPR. Entanglement and space-time geometry, long thought to be separate, may be two sides of the same coin. Imagine two particles that are entangled. They share a quantum state. Measure one, and you instantly affect the other even if it's light years away. According to EREPR, this connection is not metaphorical. It is physical. A tiny, non-traversable wormhole links Thema Bridge through space-time invisible to us, but real nonetheless. On a larger scale, consider black holes. They are the densest objects in the universe. Their gravity so intense that they tear holes in the fabric of space-time. According to general relativity, if two black holes are connected by a wormhole, they form an Einstein-Rosen bridge. According to quantum mechanics, if two black holes are entangled, their shared state implies deep, instantaneous correlation. EREPR suggests that these are not separate facts, but the same underlying reality viewed through different lenses. This idea is not just poetic, it is powerful. It offers a potential path toward reconciling quantum mechanics with general relativity, two theories that currently exist in tension. If space-time geometry itself is emergent from quantum entanglement, then perhaps gravity is not a fundamental force, but a byproduct of deeper quantum connections. In this view, the smooth structure of space is built from a vast network of entangled particles. The strength of their entanglement determines the curvature of space-time. A highly entangled region becomes curved, like near a massive star. A weakly entangled region becomes flat. Space is not a stage, but a woven fabric of relationships. EREPR also addresses the black hole information paradox. If the interior of a black hole is connected to the radiation it emits via entangled wormholes, then perhaps information is not lost but transferred hidden in the geometry of spacetime itself. Still, the theory raises deep questions. These wormholes are not traversable. No traveler could journey through them. They are purely informational structures. What does it mean to be connected if nothing can pass through? What does it mean for reality if space is not fundamental, but emergent from correlations? These questions are not yet fully answered. EREPR remains a conjecture, not a proven fact, but it has sparked a new era of research at the boundary of quantum information and gravity. It has inspired the idea that space-time might not exist without entanglement. That tearing entanglement could literally tear space apart. Philosophically, EREPR is a revelation. It suggests that separation is an illusion, that what we see as distance is a byproduct of deeper unity. It reframes entanglement not as a curiosity, but as the scaffolding of reality. In this light, the universe is a tapestry of interwoven threads not lines on a grid, but bonds of information, loops of connection. And in every particle that shares a state with another, in every black hole that curves the cosmos, we may glimpse a wormhole. Not a portal to another world, but a window into the true architecture of existence: cosmic inflation. At the dawn of time, in the first fractions of a second after the Big Bang, the universe underwent an extraordinary transformation, so sudden, so rapid, and so immense that it reshaped the entire cosmos in less time than it takes for light to cross a single atom. This event is known as cosmic inflation, and it may be the key to understanding why the universe looks the way it does today. In the standard Big Bang model, the universe begins as an incredibly hot, dense point that expands outward. But this model, elegant as it is, leaves crucial questions unanswered. Why is the universe so uniform in all directions? Why is space so flat, as if balanced on a knife's edge? And where did the initial conditions come from? Cosmic inflation provides answers. Proposed by physicist Alan Guth in the early 1980s, the theory posits that just after the Big Bang, the universe experienced a burst of exponential expansion. Space itself expanded faster than the speed of light, not violating relativity, because nothing traveled through space. Rather, space itself grew. During this brief period, perhaps just 10⁻³ circumflex, 36 10⁻36 to 10⁻3210 circumflex, 32 10⁻32 seconds after the Big Bang, the universe inflated by a factor of at least 102,610 circumflex, 26 1026. That's like a subatomic particle expanding to the size of a galaxy in the blink of an eye. This sudden expansion smoothed out any irregularities, explaining why the cosmos appears nearly the same in all directions. The cosmic microwave background, a relic of the early universe, shows this uniformity in stunning detail. Inflation also flattened the universe. Imagine blowing up a balloon. The more you inflate it, the more the surface appears flat to a tiny ant walking on it. Likewise, the massive expansion of cosmic inflation made any initial curvature vanish, leaving behind a cosmos that is geometrically flat on large scales. But inflation does more than tidy up the early universe it plants the seeds of structure. During inflation, tiny quantum fluctuations meant differences in energy and density were stretched to cosmic scales. These fluctuations later became the scaffolding for galaxies, stars, and clusters. What began as jittery quantum randomness became the grand architecture of the universe. The idea of inflation is supported by multiple lines of observational evidence. Measurements of the cosmic microwave background reveal temperature variations that match the predictions of inflation. Large-scale structure surveys show the distribution of galaxies forming patterns that echo the early fluctuations. Yet, for all its successes, cosmic inflation remains a theory with unanswered questions. What caused inflation to start and why did it stop? What is the nature of the field, known as the inflaton, responsible for driving this expansion? These questions remain open, and physicists are searching for answers and theories that go beyond the standard model like string theory, quantum gravity, and multiverse hypotheses. Indeed, some versions of inflation suggest that it never truly ended. In a process called eternal inflation, different regions of the universe stop inflating at different times, creating bubble universes with potentially different physical laws. This leads to a multiverse, vast, possibly infinite ensemble of universes, each a variation on a theme. If true, our universe might be just one bubble in a cosmic foamon region where inflation ended and gave birth to stars, galaxies, and life. Elsewhere, inflation continues endlessly, birthing new realities beyond our comprehension. Philosophically, inflation reshapes our place in the cosmos. It tells us that our universe is not just vastids, born from a process more dynamic and strange than we once imagined. That the smoothness of the sky, the flatness of space, and the complexity of structure are not accidents, but echoes of a primordial expansion written into the fabric of reality itself. Cosmic inflation is not just a theory of the past, it is a lens through which we see the origins of order, the birth of complexity, and the subtle quantum whisper that seeded the stars. De-sitter space. Far beyond the grasp of galaxies and the reach of telescopes, there lies a vision of the cosmos, both serene and unsettling, just space-time, not teeming with stars, but expanding in silence, smooth and empty. This is de-sitter space, a solution to Einstein's equations of general relativity that describes a universe dominated not by matter or radiation, but by a mysterious, repulsive force. the cosmological constant. De Sitter space is a mathematical model of a universe filled entirely with vacuum energy, a kind of energy inherent to space itself. In this realm, gravity does not pull, it pushes. Instead of collapsing, the fabric of the cosmos stretches outward, accelerating into an ever larger, colder emptiness. To understand De Sitter space is to confront a universe where expansion has no end and no external cause. It is not driven by explosions or forces, but by the geometry of space-time itself. It is pure, elegant, and eerily relevant for our own universe, as observations now suggest, may be evolving towards such a state. In 1998, astronomers discovered that the expansion of the universe is accelerating. Distant supernovae appeared dimmer than expected, implying that galaxies are receding faster over time. This led to the startling conclusion that some unknown force node called dark energies driving this acceleration. The simplest explanation? A small positive cosmological constant, just like in De Sitter space. In this model, matter becomes increasingly irrelevant. As galaxies drift apart, the density of stars and atoms dwindles. Over time, they recede beyond our horizon, leaving behind an ocean of empty space governed by one relentless principle: exponential expansion. In the far future, if this trend continues, our universe may become indistinguishable from De Sitter space, dark, smooth, and isolated. But De Sitter space is not just a prediction. It is a testing ground for the deepest questions in theoretical physics. Unlike the familiar spacetimes of black holes or stars, De Sitter space challenges our understanding of entropy, information, and even time itself. Consider entropy's measure of disorder or information content. In black hole physics, entropy is proportional to the area of the event horizon. De Sitter space also has a horizon not around a collapsed star, but around each observer, beyond which events can never be seen. This De Sitter horizon has entropy too, and it poses deep puzzles. What information is stored on it? Is it holographic? Can it encode the entire contents of the observable universe? These questions tie De Sitter space to the holographic principle, which suggests that everything within a volume of space can be described by data encoded on its boundary. In De Sitter space, this boundary is elusive and not a physical edge, but a horizon of perception. Yet it may hold the key to understanding quantum gravity, black holes, and the deep structure of the cosmos. Philosophically, De Sitter space is sobering. It points toward a cosmic fate, not of fire, but of frost, slow, relentless stretching into silence. Stars will burn out, matter will decay, and the night sky will empty, pixel by pixel. Communication across galaxies will cease. Information will be lost behind horizons. And yet, in its stillness, De Sitter space reveals something sublime, that the universe is not merely an explosion, but a geometry. Not a flurry of events, but a curve in the grand equation of being. It reminds us that space-time is not a passive backdrop, but an active participant in the story of existence. Whether or not our universe will ultimately settle into De Sitter space remains uncertain. But as a concept, it frames the final frontier, not as a place, but as a shape of horizon, beyond which lies not destruction, but quiet endurance. It invites us to ponder a cosmos where nothingness itself grows sand in that expansion. Writes the closing chapters of Cosmic Time, the cosmic microwave background. If the universe had a memory, a record of its very first breath, it would be written not in words or matter, but in light soft, cold, and ancient. That light is the cosmic microwave background, CMB, the oldest electromagnetic radiation in existence. A fossil glow from a time when the cosmos was just 380,000 years old. Today, the CMB permeates the universe as a faint, nearly uniform background of microwave radiation. It fills every direction of the sky, invisible to the naked eye, yet measurable by delicate instruments. To look at the CMB is to peer through a window into the infant universe, to see the cosmos as it was when the first atoms formed and light could finally travel freely. In the earliest moments after the Big Bang, the universe was a seething plasma of particle shot, dense and opaque. Photons scattered endlessly off electrons, unable to travel far without colliding. It was a storm of energy with no clear line of sight. But as the universe expanded, it cooled. Eventually, the temperature dropped low enough for protons and electrons to combine into neutral hydrogen atoms, a moment known as recombination. With the formation of neutral atoms, The fog of the early universe lifted. Photons, no longer hindered by constant collisions, were set free. They began to travel outward, unimpeded, carrying with them a snapshot of the universe at that very moment. That ancient light is what we now detect as the CMB. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB appeared as a persistent noise in their radiotelescopian echo they could not explain. It turned out to be the smoking gun for the Big Bang Theory, confirming that the universe had indeed emerged from a hot, dense origin. But the CMB is more than a relic. It is a mappa blueprint of the universe's earliest structure. Though remarkably uniform, it contains tiny fluctuations in temperature differences, as small as 1 part in 100,000. These minute variations are not random noise. They are the seeds of cosmic structure. Over billions of years, under the influence of gravity, they grew into galaxies, clusters, and the vast web of cosmic architecture we observe today. Modern satellite missions like COBE, WMAP, and Planck have mapped the CMB with astonishing precision, revealing a universe that is not only uniform, but also flat, isotropic, and governed by known physical laws. From these maps, we've measured the age of the universe, the composition of matter and energy, and the initial conditions for cosmic evolution. The CMB also carries the imprint of sound acoustic oscillations rippling through the primordial plasma. These cosmic harmonics are like a symphony frozen in time, offering clues to the early dynamics of the universe. Their precise patterns have become one of the most powerful tools for cosmology. Yet, the CMB is not the end of the story, it is the beginning. By analyzing its polarization, scientists hope to detect traces of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Tiny swirls in the CMB's polarization, known as B modes, could be the fingerprints of gravitational waves from that primordial explosion. Such discoveries would connect the largest scales of existence to the tiniest bridge between quantum mechanics and general relativity, written in the language of light. Philosophically, the CMB is humbling. It reminds us that the universe remembers, that even the faintest glow, the coldest radiation, carries meaning across time and space. It tells a story that began before stars, before atoms, before memory itself, a story still unfolding in the light that bathes us every day, though we no longer see it. To hear the voice of the cosmos, we need not look far. It's all around Usen, the static between stations, in the hum of the microwaves, in the silence between stars. A message from the beginning, still echoing across eternity. Time crystals. Crystals are nature's most orderly structures, repeating, rigid, and beautiful. From snowflakes to diamonds, they exhibit spatial regularity, their atomic lattices frozen in geometric perfection. But what if this order could extend not just across space, but through time? What if a system could move endlessly, without energy, in a rhythmic dance that never ends? This is the strange promise of time crystals. Proposed in 2012 by Nobel laureate Frank Wilczek, time crystals are a new and exotic phase of matter, one that breaks not spatial symmetry, but temporal symmetry. In everyday physics, time symmetry means that the laws of nature are the same today as they were yesterday, and will be tomorrow. Time crystals defy this invariancy not by violating the laws, but by existing in a state that repeats in time, even when left undisturbed. To understand this, consider a conventional crystal. Its atoms arrange themselves in a repeating pattern in space. You can move a crystal over by a certain distance, say, one lattice unitan, it looks the same. A time crystal behaves analogously in time. If you observe it at regular intervals, it returns to the same configuration, even though no energy has been added or removed. This is not perpetual motion in the classical energy-defying sense. Time crystals do not produce work. Rather, they oscillate in their lowest energy state, a phenomenon previously thought impossible. In standard systems, motion implies energy, but time crystals dance in their ground state, shifting rhythmically without consuming fuel. The first realizations of time crystals were achieved not in nature, but in carefully controlled laboratory conditions. In 2016, physicists managed to engineer a time crystal using a chain of qubits quantum bits within a quantum computer. By applying periodic pulses, they coaxed the system into a stable, repeating pattern that persisted over time, despite environmental noise. Later experiments used trapped ions and spin systems, confirming that time crystalline behavior could emerge in diverse quantum settings. These systems showed temporal order, a regular ticking that spontaneously emerged despite being driven by uniform external forces. This spontaneous synchronization is the hallmark of a time crystal. What makes time crystals so astonishing is that they challenge fundamental assumptions about stability and equilibrium. In classical thermodynamics, systems tend to settle into equilibrium, a state of rest or maximal entropy. Time crystals, however, exist perpetually out of equilibrium. They are not static, but stable through motion. This opens the door to new realms in condensed matter physics. Time crystals may enable robust quantum memories, capable of storing information in a stable, oscillating form. They could also serve as testbeds for studying non-equilibrium phases, helping us understand complex systems like living organisms, which also maintain order far from equilibrium. The concept has sparked speculation in fields beyond physics. Could time crystals offer insight into biological rhythms? Could they help explain the persistence of time itself, or the arrow of its flow? Might they represent a deeper principle of naturon where motion and order are not opposites, but companions? Philosophically, time crystals are hauntingly poetic. They embody the paradox of eternal return of change that remains the same, of movement that requires no fuel. They hint at a universe where time is not merely a backdrop for events, but a field that can itself crystallize, structure, and resonate. In the quiet heartbeat of a time crystal, we glimpse a new kind of orderon not frozen in space, but pulsing in time. It suggests that the fabric of reality is more musical than mechanical, more cyclical than linear. And in that rhythm, perhaps we hear an echo of the deeper cadence that underlies all things. The multiverse. What if everything we know, our universe, with its galaxies, stars, and laws of physics, is just one chapter in a much vaster story? What if beyond the edge of our observable cosmos, reality continues, not just in space but in possibility, spawning countless other universes with different histories, laws, and outcomes? This grand speculation is known as the multiverse vision of existence, that extends far beyond the limits of our comprehension. The idea of a multiverse is not mere fantasy. It arises naturally from several leading theories in modern physics. In cosmology, the theory of eternal inflation suggests that after the Big Bang, inflation didn't stop everywhere at once. While inflation ended in our region of space giving rise to the universe, we see other regions kept inflating, endlessly, creating a cosmic foam of bubble universes. Each bubble could harbor its own Big Bang, its own physical constants, its own version of reality. This inflationary multiverse posits that our universe is just one bubble in an infinite frothing sea. These other bubbles may be unimaginably distant, forever unreachable, yet they may exist all the same, each a distinct realm with its own version of physics. Meanwhile, quantum mechanics provides another route to the multiverse through the many worlds interpretation. In this framework, every quantum event with multiple possible outcomes causes the universe to branch. If a particle can go left or right, it does both hatch outcome realized in a separate branch of the universe. When you flip a coin, in one world it lands heads, in another tails. Every decision, every chance event spawns new realities. These branches don't interact, but they coexist. You exist in countless versions across these worlds, each shaped by the ripple of every choice and chance. The multiverse here is not spatial, but branching a tree of realities growing from quantum roots. String theory also hints at a multiverse. It allows for a vast landscape of possible vacuum states, different ways the universe's extra dimensions could be configured. Each configuration leads to a different set of physical laws. With 1,050,010 circumflex, 510,500 or more possibilities, the string landscape suggests a staggering array of potential universes, each as real as our own. This flood of possibilities raises profound questions. Why do we find ourselves in a universe with laws so finely tuned for life? Why do constants like the strength of gravity or the charge of the electron fall within the narrow range that allows stars, chemistry, and consciousness? The multiverse offers a possible answer: anthropic selection. We live in this universe because it is one of the rare ones where observers can evolve. In a multiverse of infinite variety, Some universes will be barren, others chaotic, but a few will be just right. And it is in these rare islands of order that life emerges to ask the question, but can a theory of the multiverse be scientific? If we can never observe other universes, how can we test the idea? Critics argue that without falsifiability, the multiverse remains speculative metaphysics. Proponents counter that if our best theories predict a multiverse, then we must take it seriously, regardless of whether we can see its other branches. Philosophically, the multiverse expands the canvas of reality. It tells us that our universe is not the totality of existence, but one expression of possibility among many. It reframes uniqueness as rarity and accidents as inevitabilities across the whole. In this view, reality is not a single thread, but a vast tapestry woven from infinite threads of becoming. And though we may inhabit just one strand, the existence of others imbues our own with new perspectiva, reminder that the cosmos may be not a singular book, but a library of worlds. Entropy and the arrow of time. Time moves in one direction. Eggs break but do not unbreak. Smoke rises and disperses, never reassembling into a match. We remember the past, not the future. This asymmetry, the arrow of time, is so embedded in our experience that we rarely question it. Yet, in the deep language of physics, time is symmetric. The fundamental equations work equally well forward or backward. So where does the arrow come from? The answer lies in entropy, a measure of disorder, or more precisely, the number of microscopic configurations that correspond to a macroscopic state. The second law of thermodynamics tells us that in a closed system, entropy tends to increase, order decays, heat spreads, structures collapse. This statistical tendency gives time its direction not as a law, but as a vast imbalance of probability. Imagine a deck of cards. There is only one perfectly ordered sequence, but trillions of jumbled ones. Shuffle the deck, and you are vastly more likely to land in disorder. Entropy increases not because it must, but because disorder is more probable than order. The universe moves from special, low entropy states to typical, high entropy ones. That is the arrow. This principle applies to everything from melting ice to the evolution of stars, from the decay of cities to the fate of the cosmos. Entropy governs not just physical systems, but information, memory, and life itself. It defines the direction in which change feels natural. But this explanation introduces a profound question. Why did the universe start in a low entropy state? After all, the Big Bang should have been the most chaotic moment imaginable. Yet it was, paradoxically, highly ordered, smooth, dense, uniform state from which entropy could increase. This mystery remains one of the deepest in cosmology. Some suggest that the Big Bang was not the true beginning, but a transition from a previous phase. Others posit that inflation, by smoothing out the universe, set the initial conditions for entropy to rise. Yet none of these answers fully explain why time should have a preferred direction at all. Entropy also challenges our notions of determinism. In classical mechanics, the future and past are equally determined. But entropy introduces irreversibility. Even if we could know every atom's position, we could not rewind the universe, because the macroscopic configuration is only one of many possibilities. Entropy conceals the past in a fog of likelihoods. In quantum mechanics, this interplay becomes even more subtle. Measurement introduces a kind of temporal asymmetry. Wave functions collapse, entanglement spreads, and information becomes entangled with the environment, another form of entropy increase. Even the act of observation is a one-way street. Some theorists explore whether the arrow of time might emerge from the perspective of observers within the system. We experience time as flowing from past to future because our memories, cognition, and records all encode increasing entropy. It is not that time flows, but that we, as beings of structure and information, are built to move in one direction. Entropy also defines the future. Stars will burn out, galaxies will drift apart, black holes will evaporate. In the distant ages to come, the universe may fade into a featureless void, a heat death of maximal entropy, where no work can be done and no structure can form. This is not destruction, but thermodynamic stillness. Yet, within this fate, entropy is not only a force of decay, it is a precondition for complexity. Life exists in the gradient between order and disorder. Stars shine by converting mass into energy, increasing entropy. Planets warm, oceans churn, and biology arises in the flow of heat. Without entropy, there would be no time but also no life, no memory, no change. The arrow of time, born from entropy, is not just a feature of physics. It is the river we inhabit, and as we drift upon it, measuring change, marking loss, building meaning, we find that time is not just a dimension but the very rhythm of existence. Virtual particles. In the silent vacuum of space, where nothing seems to stir, there is a secret commotion flickers of energy, bursts of presence, pairs of particles blinking into and out of existence. These are virtual particles, the ghosts of quantum fields, ephemeral and unobservable, yet fundamental to the very structure of reality. According to classical intuition, a vacuum is empty, but quantum field theory rewrites that notion entirely. In this framework, every type of particle is a vibration of an underlying field that pervades space. Even in the absence of real particles, these fields cannot remain perfectly still. They quiver with quantum fluctuations uncertainties that prevent total silence. From these fluctuations arise virtual particles, transient disturbances in the field that exist for an instant before annihilating. They are not directly detectable, they do not leave trails or flash on screens, but their presence is felt in subtle, profound ways. They shape the behavior of real particles, mediate forces, and influence the vacuum itself. Take the electromagnetic force. It is mediated by photons, but not only by the real, traveling ones that form beams of light. Virtual photons fleeting in internal layer constantly exchange between charged particles, creating the force we call electromagnetism. Though we never see them, they form the scaffolding of interaction. One of the most vivid consequences of virtual particles is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience an attractive force not because of any classical interaction, but because the virtual particles between them are constrained. Outside the plates, the vacuum teems with fluctuations. Between them, fewer modes are allowed. The imbalance creates pressure, pushing the plates together. This force, measured and verified, is a manifestation of the quantum vacuum. Virtual particles also play a role in the decay of particles, in the shifting of energy levels in atoms, as in the Lamb shift, and in the corrections of interactions known as quantum loop effects. These adjustments, calculated through the mathematics of quantum electrodynamics, QED, yield predictions that match experiment to astonishing precision, sometimes to more than 10 decimal places. But perhaps the most dramatic role of virtual particles is found near black holes. According to Stephen Hawking's groundbreaking work, the intense gravity near a black hole's event horizon can pull apart virtual particle pairs before they annihilate. One particle falls in, the other escapes. From the outside, it appears as if the black hole is emitting radiation, what we now call Hawking radiation. Over vast time, this slow leak could evaporate the black hole entirely. An effect rooted in virtual phenomena may decide the fate of these cosmic giants. Despite their utility, virtual particles raise philosophical questions. If they cannot be directly observed, are they real? Some physicists argue they are merely mathematical tools, artifacts of perturbative calculations. Others insist that while fleeting, their effects prove their existence in the deepest operational sense. Virtual particles challenge our notion of what it means to exist. They are not stable entities with trajectories, but flickers of probability within fields that never sleep. They remind us that the vacuum is not nothing, but a seething, restless potentiala, ground state humming with possibilities. In this quantum view, the universe is not a stage of empty space upon which particles play, but a web of fields, ever active, ever fluctuating. What appears to us as void is, in fact, fullness. What seems silent is alive with whispers. Virtual particles are the breath between words in the language of the cosmos. They are the glimmer at the edge of being, the suggestion of presence before presence becomes real. In their fleeting nature, they reveal the depth of the quantum world, a world where even nothing is never truly nothing. The holographic principle. What if the universe we experience the vastness of space, the motion of time, the tapestry of stars and matter is not the ultimate reality, but a projection? What if everything we perceive in 3 dimensions is encoded on a distant 2-dimensional surface, like a cosmic hologram? This is the essence of the holographic principle, one of the most radical and profound ideas to emerge from theoretical physics. The holographic principle suggests that all the information contained within a volume of space can be described by data stored on its boundary. It proposes that our three-dimensional universe may arise from a lower dimensional structure, much like a hologram is formed by a two-dimensional film that encodes a full 3D image. This notion arose from black hole thermodynamics. In the 1970s, Jacob Bekenstein discovered that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon, the surface, that marks the point of no return. Stephen Hawking's work confirmed this, showing that black holes emit radiation and thus have a finite entropy. This area scaling property of entropy was deeply strange. Normally, entropy scales with volume e, more space, the more room for disorder. But with black holes, the limit was set by the surface. This led to a tantalizing possibility that the true degrees of freedom, the ultimate building blocks of nature, might reside on surfaces, not within volumes. In the 1990s, physicist Gerard Hooft proposed that this principle might extend to the entire universe. Leonard Susskind expanded the idea, arguing that if it holds for black holes, it could be true for all of spacetime. The holographic principle was born a bold assertion that our world might be fundamentally two-dimensional at its core. The principle gained mathematical grounding through the ADS-CFT correspondence discovered by Juan Maldacena. This duality connects two seemingly different theories: a gravitational theory in a curved bulk spacetime, anti-de Sitter space, and a quantum field theory without gravity on its flat boundary. Everything happening in the higher dimensional bulk has an equivalent description in the lower dimensional boundary. They are two versions of the same reality. Though our universe is not anti-de Sitter in shape, this correspondence offers a blueprint to a working model of holography that suggests the universe itself could be encoded on a cosmic screen far removed from where we perceive it. This idea reshapes our understanding of space, information, and physics. If the holographic principle is true, then space is not fundamental. It is emergent result of deeper informational structures. Just as a hologram creates depth from encoded interference patterns, our experience of distance and geometry may arise from correlations on a boundary. It also touches on quantum gravity and the nature of black holes. The principle offers a potential solution to the black hole information paradox. If information is never lost, but stored on the horizon and eventually released via Hawking radiation, then unitarity the principle that quantum processes are reversibly preserved. Philosophically, the holographic principle is both dizzying and liberating. It tells us that what we call reality may be a shadow, a projection from a deeper truth. It echoes ancient metaphors Plato's cave, where prisoners perceive only the shadows on the wall, mistaking them for the real world. But unlike metaphor, the holographic principle is rooted in mathematics, in entropy, in geometry. It asks us to rethink not only the fabric of space, but the essence of existence. What if the world is not a container of things, but an encoding of relationships? In the flicker of stars and the motion of galaxies, in the structure of atoms and the dance of fields, perhaps what we are truly witnessing is the unfolding of a code not confined by space, but written on its edge. A hologram of being projected into the theater of perception, Planck, time, and length. At the heart of the universe, beneath the whir of atoms and the pulse of stars, lie the most fundamental scales of space and time, Planck length and Planck time. These are not simply small measurements. They are boundaries beyond which our understanding dissolves, thresholds that mark the edge of known physics and hint at the quantum fabric from which reality itself is woven. The Planck length is the smallest meaningful unit of distance, approximately 1.616 times 10 minus 351.616 times 10 circumflex, 1.616 times 10 minus 35 meters. It is unimaginably 10 smaller than a proton by a factor of 102,010 circumflex, 21,020. At this scale, our classical concepts of geometry break down. Space is no longer smooth and continuous, but becomes grainy, fluctuating with quantum uncertainty. Similarly, Planck time around 5.39 times 10 minus 400 and 45.39 times 10 circumflex, 5.39 times 10 minus 44 seconds is the smallest meaningful unit of time. It represents the time it would take for light to travel one Planck length in a vacuum. Below this interval, the idea of before and after may cease to have physical meaning. Time becomes foamy, stochastic, perhaps even illusory. These values are not arbitrary. They arise naturally from three fundamental constants: the speed of light CCC, the gravitational constant GGG, and Planck's constant HHH. By combining them, Max Planck in the late 19th century derived natural units that encode the scales where quantum mechanics and gravity must merge. At the Planck scale, gravity becomes as strong as the other fundamental forces, and space-time itself becomes quantum. Fluctuations are so extreme that the fabric of the universe may resemble a turbulent sea filled with miniature black holes, wormholes, and violent distortions of realm known as quantum foam. But this domain is hidden from direct observation. Our most powerful microscopes and particle accelerators fall woefully short of probing such scales. The energies required to examine distances at the Planck length are beyond anything we can currently achieve, comparable to those present in the earliest moments after the Big Bang. Yet the Planck scale is not irrelevant. It serves as a compass for theory. It marks where our best physical descriptions, general relativity, and quantum mechanics both apply and both fail. The search for a theory of quantum gravity, a unifying framework that harmonizes the large and the small, is driven by the need to describe reality at this scale. String theory, for example, posits that the fundamental constituents of nature are not particles but tiny vibrating strings, their size on the order of the Planck length. Loop quantum gravity envisions space as a network of discrete loops, each with Planck scale volume. These theories, while speculative, attempt to tame the wildness of the quantum gravitational regime. The implications of the Planck scale are profound. If space and time are quantized, then the universe is not a continuum, but a digital constructed lattice of information. Geometry becomes emergent, causality, probabilistic. Concepts like position, trajectory, and locality lose their classical meaning. Moreover, the Planck array the first moments after the Big Bang remains a frontier of mystery. Within this blink of time, all forces were unified. The universe was hot beyond comprehension, and quantum gravity reigned. Understanding this era may unlock the story of the universe's birth not merely as an event, but as a transition from timeless quantum potential to space-time actuality. Philosophically, the Planck scale invites humility. It reminds us that our senses and tools touch only the surface of being. Beneath the visible world, reality pulses with a logic more elemental, more abstract than geometry or duration. In contemplating the Planck length and time, we are peering into the roots of existence, see not just into smaller pieces, but into a different kind of reality. One where space is not a container and time is not a flow, but both emerge from something deeper, stranger, and more fundamental than we have yet imagined. Primordial gravity waves long before the first atom formed. Before the light of stars pierced the darkness, the universe trembled. These earliest ripple echoes from the birth of space and time were not made of sound or light, but of gravity itself. They are known as primordial gravity waves, and they may carry the first message ever etched into the cosmos. Gravitational waves are distortions in the fabric of space-time, predicted by Einstein's general relativity. When massive objects accelerate like black holes merging or neutron stars colliding, they send out ripples, like stones dropped in a pond. These waves travel at the speed of light, stretching and compressing space as they go. But long before stars or galaxies existed, something else may have stirred the cosmos: inflation. In the first instant after the Big Bang, the universe expanded exponentially, inflating by many orders of magnitude in a fraction of a second. This explosive growth wasn't smooth. It was turbulent, filled with quantum fluctuations, and among these were fluctuations in space-time itself. These primordial fluctuations generated gravity waves, weak, subtle, and pervasive. Unlike gravitational waves produced by collapsing stars, primordial gravity waves are not localized events, but a cosmic background of faint hum left behind by the birth of the universe. They permeate all of space, relics from the first trillionth of a second. Detecting these waves is a formidable challenge. They are incredibly faint, stretching the fabric of the cosmos by fractions of a proton's width, but they may have left fingerprints, swirls in the polarization of the cosmic microwave background. These patterns, known as BMOs, are signatures of the twisting, curling effect gravity waves would have on light released shortly after the Big Bang. In 2014, the BICEP 2 experiment announced a potential detection of such B modes, sparking excitement and speculation that we had finally glimpsed the quantum echo of inflation. But further analysis showed the signal was contaminated by galactic dust. Still, the quest continues with more sensitive telescopes, better data, and renewed hope. Why are these waves so important? Because they probe physics at energies far beyond any particle accelerator. They could confirm inflation, reveal the nature of the inflaton field, and offer insights into grand, unified theories models that aim to unite the fundamental forces of nature. They might even hint at quantum gravity, string theory, or the multiverse. Primordial gravity waves are also unique in their independence. Unlike matter and light, they interact very weakly with the universe. They pass through everything unaffected by plasma, dust, or radiation. This makes them pristine messenger sonoturt since the moment they formed. If we detect them, we will have built a time machine of sorts, not one that travels through time, but one that listens to its earliest rhythm, a way to hear the whisper that set the universe in motion. Philosophically, these waves stir something profound. They are not echoes of stars or galaxies, but of time's beginning. They remind us that the universe was never silent, that it has always been in motion, always pulsing, even before it had form or light. To seek them is to seek the origin of structure, the pattern beneath the chaos, the ripple before the wave. It is to listen to the birth cry of the cosmos, stretched across eternity, still vibrating in the void. In those faint ancient undulations, we may find not just evidence of inflation or quantum fields, but something deeper, a signature of becoming, an imprint of the transition from the void to existence, from stillness to motion, from possibility to reality. Axions. Among the countless particles that populate the theoretical realms of physics, few are as elusive and enigmatic as axions. Born not from collision experiments but from elegant mathematical necessity, axions remain one of the most compelling candidates for dark matter and possibly a key to unlocking the universe's deepest symmetries. The story of axions begins with a puzzle in quantum chromodynamics, QCD, the theory that describes the strong nuclear force, the interaction that binds quarks inside protons and neutrons. This theory allows, in principle, for a certain kind of asymmetry, a violation of the combined symmetries of charge conjugation, C, and parity, P, known collectively as CP violation. But experiments show that the strong force respects CP symmetry to a remarkable degree. It should violate it, but doesn't. Why not? This is the strong CP problemone of the great theoretical mysteries of modern physics. To resolve this, Roberto Pache and Helen Quinn proposed a new symmetry in the late 1970s, which would naturally set the CP violating term in QCD to zero. From this symmetry emerged a new particle, the axion, named by Frank Wilczek after a popular laundry detergent because it cleaned up the theory. Actions, if they exist, would be extremely light, electrically neutral, and interact only very weakly with ordinary matter. They would rarely be produced in particle collisions and would slip undetected through detector straits that make them nearly invisible. Yet these same properties also make axions perfect dark matter candidates. Dark matter is the unseen mass that tugs on galaxies, bends light from distant stars, and shapes the large-scale structure of the cosmos. Despite its gravitational influence, we've never directly observed it. Actions could be this invisible glue, permeating the universe in a vast, diffuse halo around galaxies, influencing their rotation without emitting a single photon. Actions are not alone in the search for dark matter, but they offer a unique blend of theoretical elegance and cosmic utility. They could be produced in the early universe in sufficient abundance to account for dark matter, and their cold, slow-moving nature fits the observations of how galaxies cluster and evolve. Searching for axions is a technical and imaginative challenge. Because they are so weakly interacting, scientists use exquisitely sensitive instruments. One method involves placing a strong magnetic field in a cavity resonator and listening for a faint electromagnetic signal of photon born from the conversion of an axion in the presence of a magnetic field. Experiments like ADMX, Axion Dark Matter Experiment, and future designs hope to capture these whispers from the dark. Other approaches involve searching for axion-like particles in astrophysical data, studying the polarization of starlight, or investigating the cooling rates of stars, which might emit axions as a subtle energy drain. Yet the search is not merely about finding a particle. It's about revealing a hidden order in the universe. If axions are found, they will solve the strong CP problem, unveil the nature of dark matter, and mark a profound unification of the smallest scales of quantum fields with the largest scales of cosmic structure. Philosophically, axions invite us to ponder the unseen. They are a symbol of subtlety of a universe whose most influential forces may lie beyond detection, yet shape everything. They remind us that mystery is not always loud or chaotic. Sometimes it is quiet, persistent, and woven into the background of reality. To seek the axion is to follow a whisper in the darker thread of symmetry, delicately spun, connecting the quantum to the cosmic, the precise to the profound. Cosmic strings. Stretching across the void, like hairline fractures in the fabric of space, cosmic strings are hypothetical remnants from the earliest moments of the universe, infinitesimally thin, yet unimaginably dense. They are not strings in the everyday sense, but topological defects, scars left behind as the universe cooled and its fields crystallized into structure. To grasp the concept, consider how water freezes. As it transitions from liquid to solid, it forms ice crystals, rigid structures that sometimes trap imperfections or mismatched boundaries. Now imagine the early universe, a cauldron of high-energy fields, undergoing a similar kind of phase transition as it expanded and cooled. In this analogy, cosmic strings are the imperfections, the misaligned edges where regions of the cosmos froze into different configurations. Cosmic strings are predicted by certain grand unified theories, guts, which attempt to merge the strong, weak, and electromagnetic forces into a single framework. During symmetry-breaking events in the early universe, these theories suggest that defects like monopoles, domain walls, or strings might have formed. Of these, cosmic strings are perhaps the most enduring and potentially observable. These strings, if they exist, are incredibly narrow, perhaps a millionth of a billionth of a billionth of a meter across, but a single centimeter of one would outweigh Mount Everest. They could stretch for thousands or millions of light years, coiling through the cosmos, moving at nearly the speed of light, creating wakes in space-time itself. Cosmic strings are not to be confused with the strings of string theory. While both involve fundamental structures, cosmic strings are macroscopic relics from symmetry breaking, not vibrating quantum objects. Yet their implications are just as profound. One way to detect cosmic strings is through their gravitational effects. Because they are so massive, they would distort the space-time around them, acting as gravitational lenses. A cosmic string passing between Earth and a distant galaxy could duplicate or shift the image, bending light like a cosmic mirror. Such events would be rare, but potentially observable. Another signature might be in the gravitational waves they emit. As strings move and interact, they can form loops which oscillate and radiate energy. These gravitational wave bursts could be picked up by sensitive detectors like LIGO, Virgo, or future space-based observatories. They would not sound like black hole collisions, but more like sharp, transient chirpsicos of primordial tension. Cosmic strings could also influence the cosmic microwave background. Their presence might leave faint imprints, linear discontinuities, or patterns in temperature fluctuations. Though no definitive signs have yet been found, ongoing surveys continue to probe the sky for these subtle traces. The potential existence of cosmic strings raises deep questions. If they are discovered, they would offer direct evidence of high-energy physics far beyond the reach of terrestrial experiments on archaeological artifact from the universe's earliest seconds. They could reveal how fundamental symmetries were broken, how forces split, and how the early universe took shape. Even without direct detection, the search shapes our theories. It guides the development of models that unify the known forces, challenges assumptions about the smoothness of the cosmos, and connects cosmology to particle physics in a dynamic and interactive way. Philosophically, cosmic strings are symbols of continuity and fracture. They represent the idea that the universe is not born smooth, but scarred by its own history. That in the vast silence of space, hidden chords may still vibrate with the memory of creation. To seek them is to search for the seams of reality, for the stitching that holds together the grand design. And in finding them, we may touch a thread that stretches from the beginning of time to the farthest edge of space, the fabric of space-time. Space and time, once thought of as separate, immutable backdrops to all existence, are now understood as a single, dynamic entity, space-time. This unified fabric is not merely a passive stage upon which the drama of the universe unfolds. It is an actor in its own right, curving, stretching, and trembling in response to the presence of matter and energy. Einstein's general theory of relativity introduced this revolutionary idea. Space and time are intertwined dimensions that form a flexible geometry. When a massive object like a star or planet appears, it doesn't simply sit in empty space, it bends the space-time around it. This curvature is what we experience as gravity. The Earth orbits the Sun not because it is pulled by an invisible force, but because it follows a straight path through curved space-time. Likewise, light bends around galaxies, not because it changes direction, but because the space through which it travels is warped. The fabric of space-time is smooth and continuous at everyday scales, but as we zoom into the smallest realms, quantum mechanics begins to interfere. Fluctuations arise. At the Planck scale, space-time may no longer be smooth at all. It could become turbulent, frothing with quantum activity, laced with tiny wormholes and abrupt changes in topology. This idea, still speculative, leads physicists to seek a quantum theory of gravity, one that can describe how space-time behaves under extreme conditions. Gravitational waves ripples in space-time caused by massive, accelerating objects solve for a new way to study this fabric directly. Detected for the first time in 2015, these waves confirmed a century-old prediction of Einstein's theory. They ripple across the cosmos, passing through galaxies, stars, and planets, subtly distorting distances and revealing cataclysmic events like black hole collisions. In these waves, space-time sings, but space-time is not just shaped by matter, it may itself give rise to matter and energy. Some theories suggest that particles and forces are emergent phenomena, arising from the structure and vibrations of space-time at the smallest scales. In this view, what we call reality may be a projection of deeper geometric truths. Perhaps even time itself is not fundamental, but emerges from correlations and entanglement between parts of a deeper, timeless structure. This concept is echoed in approaches like loop quantum gravity, which describes space-time as a network of finite loops, discrete units of volume and area that weave together to form the continuum we experience. Similarly, string theory envisions space-time as a higher dimensional landscape, shaped by vibrating strings whose modes of resonance determine the nature of particles and forces. As we contemplate black holes, we encounter the limits of our understanding. At their centers lie singularities, regions where the curvature of space-time becomes infinite and our equations break down. Here, the known laws of physics falter, and a quantum theory of space-time becomes not a luxury, but a necessity. The behavior of space-time in such regions holds the key to a deeper understanding of the universe. Space-time is not static. The universe is expanding, and the fabric of space-time is stretching. This expansion is not like objects flying through space. It is space itself growing. Galaxies are not moving through a pre-existing void. They are being carried apart as the very medium between them enlarges. Philosophically, the idea of space-time as a fabric blurs the line between presence and motion, between substance and relation. Space is not an emptiness, and time is not a ticking clock. They are properties of the universe, shaped by its contents and in turn shaping all that occurs within. To understand space-time is to understand the stage, the structure, and the symphony of reality. It is the silent partner in every interaction, the invisible architecture behind every star, every thought, every heartbeat. And within its folds may lie answers to questions we've only begun to ask. Non-commutative geometry. At the intersection of mathematics and physics, where space is no longer smooth and coordinates may resist conventional interpretation, lies a radical reimagining of geometry. Non-commutative geometry. This abstract yet profound idea suggests that at the smallest scales of nature, the fabric of space may not follow the familiar rules we expect. Coordinates may not commute, positions may blur, geometry itself may become quantum. In ordinary geometry, the order in which we measure dimensions doesn't matter. If you move right and then forward, you end up at the same spot as if you had moved forward and then right. This symmetry reflects the commutative nature of classical coordinates. But in the quantum realm, such neatness dissolves. Particles do not have definite positions and momenta simultaneously. Their properties are encoded in operators that do not necessarily commute. Inspired by this, non-commutative geometry redefines space not as a set of points with distances, but as an algebra of operators language where multiplication depends on order and where space behaves more like a quantum system than a classical map. It was developed in depth by mathematician Alain Connes, who envisioned a new way to describe the fabric of reality, one where the tools of quantum mechanics and geometry are not separate but fundamentally intertwined. In this framework, space is encoded by non-commuting variables, similar to the operators in quantum mechanics. Instead of working with points and lines, one works with algebras and matrices. With spectral triples and operator spaces, geometry becomes a function of relationships, not locations. The familiar concepts of curvature, distance, and dimensionality still exist, but they emerge from the spectral properties of these abstract algebras. This approach has profound implications for physics. It offers a natural setting for merging quantum mechanics with general relativity, especially in regimes where space-time becomes turbulent and non-continuous, such as near singularities or at the Planck scale. In such extreme conditions, traditional coordinates may lose their meaning, and non-commutative geometry may provide the language needed to describe what remains. One key insight is that non-commutative spaces can encode internal degrees of freedom. In particle physics, this could help explain why particles come in families, why forces behave as they do, and how symmetries are broken. By extending space-time with a discrete, non-commutative structure, some versions of the standard model can be derived from geometric principles, rather than imposed by hand. Non-commutative geometry also plays a role in string theory and quantum field theory. In certain limits, the coordinates of strings become non-commutative, blurring into one another and forming a space where locality itself becomes uncertain. These effects are not just mathematical curiosities. They might be essential features of nature at the smallest scales. Even the notion of causality becomes delicate in non-commutative settings. When positions are smeared, the idea of a clear, linear sequence of events begins to fade. This doesn't mean chaos, it means a richer, subtler logic, where events unfold not just in time and space, but within an algebra of possibilities. Philosophically, non-commutative geometry challenges our deepest assumptions about space. It suggests that the smooth continuum we experience may be an emergent illusion, a macroscopic approximation of something inherently fuzzy and relational. Space, in this view, is not a void to be filled, but a web of interactions, a stage defined by how things affect each other. To explore non-commutative geometry is to enter a realm where the line between mathematics and metaphysics blurs, where structure is encoded in symmetries, and where the invisible scaffolding of reality is written not in points, but in spectra. It invites us to reimagine what it means to measure, to move, and ultimately, to exist. 0 point energy. Even in the coldest, darkest void imaginable, where all motion has ceased and every atom lies still, the universe is never truly at rest. Beneath the silence, beneath the stillness, there hums a residual vibrational flicker of energy that cannot be removed. This is 0 point energy, the lowest possible energy state of a quantum system, and a reminder that emptiness itself is never truly empty. 0 point energy arises naturally from quantum mechanics. In classical physics, a particle in a potential well can sit motionless at the bottom, its energy 0. But in quantum mechanics, Heisenberg's uncertainty principle forbids such stillness. Position and momentum cannot both be precisely known, so a particle can never be completely at rest. Even in its ground state, the state of minimum energy, it continues to jitter, trapped in a perpetual dance of uncertainty. This persistent motion generates 0 point energy. It is present in every atom, every molecule, and every quantum field. Even a vacuum, devoid of particles and radiation, teems with fluctuating field sand and visible sea of energy, pulsing with possibility. Virtual particles flicker into existence and vanish again. Forces emerge and recede. The vacuum is alive. The Casimir effect offers one of the most striking demonstrations of 0 point energy. When two uncharged metal plates are placed very close together in a vacuum, they experience a measurable attractive force. This force arises not from classical physics, but from the suppression of certain vacuum fluctuations between the plates. The energy density outside is slightly greater than inside, pushing the plates together. It is a direct, physical consequence of the vacuum's irreducible energy. Zero-point energy also appears in the structure of matter. It contributes to the stability of atoms, the properties of liquids like helium at ultra-low temperatures, and even the behavior of biological systems. It is not an exotic anomaly. It's foundational, woven into the very architecture of the universe. But the implications of zero-point energy extend far beyond the laboratory. When applied to quantum fields in cosmology, it leads to a staggering prediction. The vacuum should have an enormous energy density enough to rip the universe apart. Yet the observed value, inferred from the accelerating expansion of the universe, is tiny in comparison. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved puzzles in theoretical physics. Some believe zero-point energy could help explain dark energy, the mysterious force driving cosmic acceleration. Others speculate about its role in the early universe, in inflation, or in the dynamics of quantum gravity. The challenge lies in reconciling quantum field theory with general relativity, in defining what vacuum energy means in curved spacetime, and in understanding whether it truly gravitates. Beyond science, zero-point energy has captured the imagination of inventors, mystics, and futurists. It is sometimes invoked in speculative claims about limitless energy or propulsion technologies, though no credible method has yet been found to extract usable energy from the vacuum without violating the laws of thermodynamics. Still, the idea that every point in space contains energy in infinite reservoir, a background hum of creation, has profound philosophical resonance. It suggests that being is never truly passive, that stillness is an illusion, and that the cosmos, even in its quietest moments, vibrates with potential. Zero-point energy is the heartbeat of the quantum world. It is the breath that fills the void, the glow that persists in darkness, the whisper beneath the silence. It tells us that the universe is never empty, never still, and that within the quietest depths of space, the dance of existence never ends. Anthropic principle. Why is the universe the way it is? Why do the constants of nature, the strength of gravity, the mass of the electron, the rate of cosmic expansion fall within the narrow range that permits galaxies, stars, planets, and life? Why is the cosmos not a chaotic storm of particles or an empty void of sterile silence? These questions bring us to the anthropic principally controversial yet compelling idea that connects the fabric of the universe with the fact of our own existence. The anthropic principle begins with an observation. The universe appears finely tuned. Change the gravitational constant slightly and stars cannot form. Adjust the electromagnetic force and atoms become unstable. Increase the rate of cosmic inflation and galaxies never coalesce. The probability of such precise conditions arising by chance seems vanishingly small. Some take this as evidence of designing a universe crafted with intention. Others reject such notions, seeking explanations within natural law or multiverse theories. The anthropic principle, however, offers a different route. It does not explain why the universe is finely tuned, but why we observe it as such, because if it were otherwise, we wouldn't be here to ask the question. This is the essence of the weak anthropic principle. Our observations are biased by the requirement that observers exist. Out of a vast range of possible conditions, we necessarily find ourselves in one where conditions support consciousness. In this view, the universe does not need to be designed for use it, simply needs to be one where beings like us can emerge. The strong anthropic principle goes further. It suggests that the universe must have properties that allow life to develop at some stage. It hints at a deeper relationship between life and cosmos, as though the fabric of existence is somehow aligned with the emergence of observers. Some interpretations verge on teleology, while others explore it in the context of cosmological models. In a multiverse scenario, the anthropic principle becomes statistical. If there are countless universes, each with different physical constants and initial conditions, then it is not surprising that at least one supports life. We live in that one not because it is special, but because it is habitable. It is like finding yourself on a planet that supports life and realizing it is the only kind you could inhabit. Critics argue that the anthropic principle is tautological, explaining too little by saying too little. It seems to dodge deeper inquiry by appealing to selection bias. Yet, when combined with theoretical models like eternal inflation or string theory's landscape of possible vacua, it offers a framework for understanding fine-tuning in a probabilistic way. Some physicists see value in its utility. The anthropic principle doesn't explain everything, but it may set constraints. It can help rule out theories that fail to produce life-permitting conditions. It offers a philosophical lens for interpreting cosmic parameters that seem arbitrary. Beyond physics, the anthropic principle touches on existential reflection. It frames humanity not as an accident, nor as a cosmic inevitability, but as an emergent feature of conditions that happen to allow complexity. We are not separate from the universe, but expressions of its structure thoughts arising within a vast and ancient mind. It also raises questions of uniqueness. If intelligent life is rare, perhaps the universe is mostly silent, and our consciousness an improbable bloom in a barren field. Or perhaps life is abundant, and the universe is a garden, vast and fertile. Either way, the anthropic principle reminds us that observation is not passive. To observe the universe is to be part of it, shaped by it, required by it. In pondering why the universe fits us so well, we glimpse the possibility that we, in turn, fit it not by chance, nor by design, but by necessity. And that necessity may be the most profound kind of meaning there is: quantum entanglement. At the heart of quantum mechanics lies a phenomenon so mysterious, so profoundly non-local, that Einstein himself called it spooky action at a distance. This is quantum entanglement, a strange and beautiful connection that links particles across space and time, binding them in a shared fate that defies classical explanation. Entanglement occurs when two or more particles become correlated in such a way that the state of one cannot be fully described without reference to the state of the other, no matter how far apart they are. Their properties become intertwined, forming a single quantum system, even when separated by light years. Imagine creating a pair of entangled particles and sending them to opposite ends of the galaxy. Measure one, and instantly, the state of the other is determined. This doesn't mean information travels faster than light. Rather, it means the particles were never truly separate to begin with. Their connection transcends space, embedded in the quantum fabric of reality. This phenomenon is not theoretical. Entanglement has been observed and confirmed in countless experiments. Photons, electrons, atoms-entangled pairs exhibit correlations that violate classical bounds. The famous Bell tests, designed to challenge hidden variable theories, have shown again and again that quantum mechanics cannot be mimicked by local, deterministic rules. Nature, it seems, is inherently interconnected. Entanglement is not limited to particles. It is a feature of quantum systems, a resource that can be used, shared, and manipulated. In quantum information theory, entanglement is currency. It powers quantum computation, enables secure communication, and lies at the heart of teleportation protocols. In a quantum computer, entangled qubits can perform calculations in parallel, probing complex problems that classical computers struggle to approach. Quantum key distribution, which relies on entanglement, allows for unbreakable encryption. Any attempt to eavesdrop alters the system, revealing the intrusion. But entanglement is more than a tool. It is a window into the non-local structure of the universe. It suggests that the world is not built from isolated bits of matter, but from relationships, correlations, patterns that persist across separation. It points to a holistic view, where systems cannot be fully understood by examining their parts in isolation. Some theories of quantum gravity, like the holographic principle or Barter, a conjecture that relates entanglement to wormholes, suggest that spacetime itself may emerge from entangled quantum states. In this view, geometry is not fundamental entanglement. The threads that weave space together are not particles or strings, but connections between quantum systems. Entanglement also challenges our notions of causality and realism. If measurement outcomes depend on correlations with distant partners, then either information transcends space or reality isn't determined until observed, or both. The universe appears to be more about potential and probability than about fixed properties. Philosophically, entanglement invites awe. It tells us that the universe is not a machine grinding forward through local interactions, but a kind of organism where distance and separation are illusions. What happens here matters there. What we measure, we affect not in a magical sense, but in a way that reveals the participatory nature of reality. In an entangled cosmos, we are not observers peering into a detached world. We are participants in an unfolding whole. We belong not just to space and time, but to a deeper web of connections, a hidden unity that underlies the seeming multiplicity of existence. Entanglement is not just a quirk of physics, it is a reminder that everything is connected, that beneath the separateness of form lies a field of coherence, that to touch one thing may be, in some fundamental sense, to touch everything. Causal set theory. In the search for a quantum theory of gravity, a framework that unites the smooth geometry of general relativity with the discrete uncertainty of quantum mechanics' own proposal, stands out for its simplicity and elegance. Causal set theory. It begins not with the continuum of space-time, but with something more fundamental, a set of discrete elements, a web of cause and effect, a cosmos built not of points and curves, but of events and order. Causal set theory posits that space-time is not continuous, but made up of individual elements like the grains of sand on a beach or the atoms in a gas. These elements are not embedded in space, they are space. They are the fabric, not what lies within it. What gives these elements structure is causality, the sequence of influence, the relationship of before and after. Each element in a causal set is an event, and the only fundamental relation is that one event can precede another. If an event A can influence an event B, then A is in the causal past of B. This partial ordering defines the structure of space-time. There is no coordinate system, no smooth manifold, only events and the direction of cause. The beauty of causal set theory lies in its radical minimalism. From this simple network of causally related points, the familiar features of space-time dimensionality, curvature, topology are meant to emerge. The continuum we experience is a coarse approximation, like a smooth curve drawn from a cloud of dots. One of the central motivations for this approach is the Planck scale. At distances near 10 miles, 3,510 circumflex, 35 10 miles, 35 meters, the smoothness of space-time breaks down. Quantum fluctuations dominate. Rather than try to stretch general relativity into this chaotic realm, causal set theory suggests that discreteness is fundamental. It is not that space-time becomes grainy, it has always been grainy. Our sense of continuity is just an illusion born of scale. To recover familiar physics, causal set theory must reproduce general relativity at large scales. Researchers work to derive the Einstein field equations, the curvature of space, and even the expansion of the universe from statistical properties of causal sets. This remains an ongoing challenge, but progress has been made, particularly in showing how volume and curvature can emerge from counting elements and examining their causal relationships. Another intriguing aspect of causal set theory is its treatment of time. In general relativity, time is a dimension, part of a four-dimensional block universe. In causal set theory, time is more primordial. Events are born into the set, one after another, in a growth process that respects causality. This dynamic evolution, sometimes called classical sequential growth, suggests a universe that is becoming rather than statically being. This perspective resonates with certain philosophical views, process philosophy, temporal becoming, and the notion that the future is open while the past is fixed. It offers a refreshing alternative to the frozen block universe, emphasizing the flow of time not as illusion, but as a fundamental ingredient of reality. Causal set theory also hints at potential observational consequences. If spacetime is fundamentally discrete, then over cosmic distances, we might detect tiny violations of Lorentz invariance minute deviations in how light and particles travel. Such signals would be faint, but they offer a rare bridge between deep theory and experiment. Philosophically, causal set theory invites us to rethink what space and time really are, not continuous tapestries, but tapestries woven from events and relations, not smooth backdrops, but networks of becoming. It strips away the scaffolding of coordinates and geometry to reveal a deeper truth, that the universe is not built from things, but from occurrences, and that the order of those occurrences is what makes reality real. To imagine the universe as a causal set is to see it as a story, not a static book, but a growing narrative, where each new event is a word added to the page, shaped by what came before and shaping what may come next. Wormholes fold a sheet of paper. Pierce it with a pencil. The point where the pencil enters and exits becomes an elegant metaphor for something far more profound, the wormhole. A hypothetical bridge through space-time, a tunnel between distant regions of the universe, or perhaps even between different universes altogether. Wormholes tantalize physicists and dreamers alike not only because they hint at shortcuts through the cosmos, but because they stretch the very fabric of reality. The idea of wormholes arises naturally from general relativity. Einstein's equations allow for space-time geometries where two separate regions are connected by a throat. These are not merely science fiction devices, they are mathematical solutions known as Einstein-Rosen bridges, first described in 1935 by Albert Einstein and Nathan Rosen. Originally, these solutions were intended to describe particles in a purely geometric way, but they soon captured the imagination of those contemplating interstellar travel and quantum connections. A wormhole could, in theory, link two distant parts of the universe, allowing a traveler to leap across vast cosmic distances in the blink of an eye. However, these early wormholes were not traversable. They collapsed too quickly for anything, even light, to pass through. To hold one open would require exotic matter material with negative energy density and repulsive gravitational effects. Ordinary matter would not suffice. Such exotic matter is not known to exist in classical forms, but quantum field theory permits the existence of negative energy under special circumstances, such as in the Casimir effect. Building on this idea, in the late 20th century, Kip Thorne and colleagues explored the possibility of stable, traversable wormholes. These structures would allow not only communication, but potentially travel across space-time. They would not violate the speed of light locally, but by bending space-time, they could connect points faster than light would travel through flat space. This is the essence of a shortcut in curved geometry. Wormholes also raise the tantalizing possibility of time travel. If one mouth of the wormhole is accelerated to near light speed and brought back, time dilation would cause the two ends to be out of sync. Step through, and you emerge in the past or the future relative to where you began. This scenario introduces paradoxes, the grandfather paradox, causal loops, and violations of determinisms that challenge the coherence of physical law. To resolve these paradoxes, some theories suggest consistency constraints events that seem to change the past would always conspire to preserve consistency, like a self-healing narrative. Others argue that time travel, while mathematically plausible, may be physically impossible due to quantum instability or cosmic censorship. Beyond travel and paradox, wormholes touch the foundations of physics. In recent years, the ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that wormholes, Einstein-Rosen bridges, may be fundamentally connected to quantum entanglement, Einstein-Podolsky-Rosen correlations. According to this view, every entangled pair is connected by a microscopic wormhole radical unity between geometry and quantum information. This idea leads to a vision of the universe where space-time itself may emerge from entanglement and where wormholes are not rare anomalies but fundamental features of connectivity in a quantum space-time. In such a universe, distance may be an illusion, and connection the deeper truth. Philosophically, wormholes invite us to contemplate the porousness of space and time. They suggest that what seems far may be close, what seems linear may be circular, and what seems fixed may bend under the right conditions. They awaken in us a sense of wonder not just for distant stars, but for the hidden tunnels that might lie between them. Whether they exist in reality or remain mathematical ghosts, wormholes stretch our imagination and our equations, showing us that the universe, vast and strange, still holds secrets that bend the bounds of what we call possible. Black hole information paradox. At the heart of one of the greatest puzzles in modern physics lies a simple yet profound question. What happens to information when it falls into a black hole? Does it disappear forever, swallowed by a gravitational abyss? Or does it linger somehow, encoded in ways we cannot yet decipher? This is the black hole information paradoxa clash between the laws of quantum mechanics and the predictions of general relativity, and a riddle that could lead us to a deeper understanding of the universe. In classical general relativity, A black hole is a region of space-time from which nothing, not even light, can escape. When an object falls into a black hole, its information, the precise quantum state that defines itis, believed to be lost to the outside universe. Only three quantities remain observable: mass, charge, and angular momentum. Everything else, the details that distinguish a book from a planet or a person from a photon, disappears behind the event horizon. This idea is summed up in the phrase, "black holes have no hair." However, quantum mechanics insists that information cannot be destroyed. The evolution of quantum systems is unitary, meaning that the total information about a system is preserved over time. If black holes truly erase information, then one of the cornerstones of quantum theory must crumble. Thus, the paradox emerges. Two foundational theories, remarkably successful in its own domain, seem to contradict each other when confronted with black holes. The paradox deepened in the 1970s when Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation is thermal and seemingly random. It carries no information about the material that fell in. Over time, as the black hole evaporates through this radiation, it could disappear entirely, leaving behind no trace of what once existed. The information, it seems, would vanish. This scenario violates quantum principles and sparked decades of debate. Could Hawking's calculations be incomplete? Could information escape in a way we haven't yet recognized? Could it be stored on the event horizon in some holographic form? Or perhaps emerge encoded in subtle correlations within the Hawking radiation? One resolution, inspired by the holographic principle, suggests that the information is not lost, but stored on the boundary of the black hole. Just as a hologram contains a three-dimensional image encoded on a two-dimensional surface, the information about the matter that falls in might be preserved on the event horizon, subtly encoded in its quantum states. Another proposal involves black hole complementarity, the idea that different observers, one falling into the black hole and one watching from outside, perceive different but consistent realities. From the outside, information is smeared across the horizon. From the inside, it continues undisturbed. Both views are valid, yet irreconcilable in a single frame. This suggests that the paradox may lie not in physics, but in our assumptions about how to describe physical processes. Recent developments in string theory and quantum gravity, such as the AS-CFT correspondence, lend support to the idea that information is not lost. Calculations in these models show that black holes can indeed preserve information, though the precise mechanisms remain obscure. In 2019 and 2020, new work on the page curve, a prediction of how entropy should behave if information is preserved, showed results consistent with unitarity, reviving hopes that the paradox might be resolved. Philosophically, the black hole information paradox forces us to confront the boundaries of knowledge. It reveals that at the nexus of gravity and quantum theory, our understanding remains incomplete. The paradox is not merely about black holes, it is about reality, about whether the universe is ultimately lawful or capricious, knowable or opaque. To solve it is to take a step toward a unified theory of everything. To understand what black holes do to information is to understand what reality does with itself, whether it forgets or whether, in some subtle, eternal way, it remembers everything. Unruh effect. Imagine sitting in the emptiness of space, drifting gently in a vacuum colder than any laboratory chill, surrounded by stillness. Now imagine accelerating through that same space gradually, steadily, and something strange begins to happen. The void, once silent, begins to glow. A faint warmth appears where there was none. This is the Unruh effect, a startling prediction of quantum field theory that links motion, perception, and the very fabric of reality. Named after physicist William Unruh, who described it in the 1970s, the Unruh effect proposes that an accelerating observer in a vacuum will detect a bath of thermal radiation where an inertial observer detects none. In other words, acceleration creates the illusion of heat. The faster you accelerate, the warmer the vacuum appears. To understand this, consider the quantum vacuum not an empty stage, but a field of fluctuating energy, where virtual particles constantly bubble in and out of existence. These fluctuations are omnipresent but balanced, producing no net energy for an observer at rest. But acceleration disturbs this balance. From the accelerating observer's point of view, the vacuum is not symmetric. It behaves like a hot gas, filled with particles, their temperature proportional to the acceleration. This radiation is not just metaphorical. In principle, it's as real as the warmth felt from sunlight or the glow of a fire. However, the effect is incredibly subtle. The acceleration needed to produce even 1 degree of temperature is astronomical on the order of 100 2010 circumflex, 21,020 meters per second squared. Such extremes are beyond current technology, making the Unruh effect nearly impossible to measure directly. Yet the implications of the Unruh effect stretch far beyond experimental feasibility. It reinforces a central theme of modern physics, that reality is not absolute but observer-dependent. What one observer perceives as empty, another may perceive as full. Temperature, like time, is not a universal quantity. It depends on how you move. The Unruh effect is deeply connected to black hole physics. In fact, it can be seen as the flat space analog of Hawking radiation. Both phenomena arise from the same underlying principle, that event horizons, whether due to gravity or acceleration, create boundaries between what can and cannot be observed. These boundaries give rise to apparent temperature and entropy. For an accelerating observer, an event horizon appears behind thema point beyond which they can never receive information, no matter how fast they go. This horizon acts like the edge of a black hole, and just as a black hole emits radiation, so too does the accelerating frame detect particles. These insights hint at a profound unity between gravity, acceleration, and thermodynamics. They suggest that space-time and quantum fields are interwoven in such a way that geometry itself has a thermal character. The very act of carving out part of a field by hiding a region behind a horizon creates temperature. It is not heat from a source, but heat from limitation, from lost information. Philosophically, the Unruh effect invites reflection on the relativity of experience. It tells us that perception is shaped not only by location, but by motion. That even in a universe governed by fixed laws, what you see depends on how you travel. It reminds us that reality, at its most fundamental level, is not a static picture, but a dynamic interplay between observer and observed. To explore the Unruh effect is to glimpse the quantum whisper beneath acceleration, to realize that stillness and motion are not merely states of matter, but states of awareness. That in the vacuum of space, the boundaries of experience are as real as any star. Time crystals. In the conventional world, crystals are marvels of symmetry and stillness structures that repeat themselves in space with perfect regularity. Their atoms form lattices, repeating patterns that make diamonds hard and snowflakes beautiful. But in the quantum world, a stranger symmetry emerges, one that unfolds not in space, but in time. This is the domain of time crystal systems that pulse, oscillate, and repeat without consuming energy, not across distance, but through the rhythm of time itself. The idea of time crystals was first proposed by Nobel laureate Frank Wilczek in 2012. He wondered, could a system exhibit motion in its lowest energy state, its ground state? Could something move forever, not because of external energy or imbalance, but because of its internal structure and the laws of quantum mechanics? At first glance, this seemed impossible. According to thermodynamics, perpetual motion in a system at its ground state violates the principle that such a state must be static and minimal in energy. Yet, in the strange logic of quantum physics, time crystals became theoretically permissible not as machines, but as systems that break time translation symmetry. Just as ordinary crystals break the symmetry of space by forming a periodic structure, time crystals break the symmetry of time by repeating their behavior at regular intervals. But the key is that they do so in a way that is stable, coherent, and requires no energy input. Their motion is not driven, it is a property of their quantum state. For years, time crystals remained a theoretical curiosity. But in 2016 and 2017, physicists created experimental versions using carefully engineered quantum systems. One approach involved chains of trapped ions manipulated by lasers. Another used a lattice of spins in a diamond, driven periodically by microwave pulses. These systems exhibited behavior that matched the criteria for time crystals, a response that repeats with a period longer than the driving frequency and resistance to decoherence. These time crystals don't spin endlessly like wheels. Instead, they exhibit discrete time symmetry breaking. If you perturb them at a regular interval, say, once every second, they respond at a different interval, say, every 2 seconds. This kind of temporal echo, locked into a specific phase, continues indefinitely without decay. It's not motion in the classical sense, but persistence in a deeper layer of order. The implications of time crystals are still being explored. In condensed matter physics, they may offer new forms of stability and coherence, useful for quantum computing and memory. Because they are robust against certain types of noise, they could serve as reliable platforms for processing quantum information over time. On a more speculative front, time crystals challenge our understanding of time itself. If symmetry can be broken in time as well as space, then time may not be as uniform or passive as we assume. It may possess structure, rhythm, and phasic qualities we associate with music more than mechanics. Some researchers even wonder if time crystals might have cosmological analogs. Could aspects of the early universe have involved time-structured fields? Could the arrow of time itself emerge from broken symmetries of temporal order? These are open questions, and they push the boundaries of both physics and philosophy. Time crystals also blur the line between motion and stillness. In a classical ground state, stillness is expected. But in a time crystal, the ground state dances not randomly, but with perfect choreography. It's as if the universe allows for stillness that sings, a silence that pulses with invisible rhythm. To contemplate time crystals is to entertain a new kind of orderon that does not persist in space, but in time. One that reminds us that time is not just a backdrop for change, but a medium in which new forms of symmetry and perhaps beauty can arise. The information universe. What if the universe is not made of particles or waves, not fundamentally built from matter or energy, but from information? Not just a metaphor or an analogy, but a literal proposal that the most basic substance of the cosmos is data, bits, quanta of knowledge woven into the structure of space and time. This idea that the universe is an information processing system has emerged from the crossroads of physics, computer science, and philosophy, and it is changing the way we think about reality itself. The roots of this view trace back to pioneers like John Archibald Wheeler, who famously proposed the phrase "it from bit." According to Wheeler, every physical entity, it ultimately derives its meaning and existence from binary yes or no decisions, from bits. Reality, he suggested, is not built from things, but from answers to questions. Existence emerges from inquiry, from observation, from interaction. In modern terms, this perspective sees the universe as a kind of quantum computer. Each interaction, each particle, each force carries and transforms information. The laws of physics become rules of data flow. The evolution of the cosmos becomes a vast computation. The wave function encodes probabilities. Measurements extract outcomes. Entanglement becomes a form of data linkage, more fundamental than distance or mass. This information-centric view gains traction in quantum gravity and black hole physics. In the black hole information paradox, the fate of information becomes a central question. Does a black hole destroy the data it swallows, or does that information somehow survive, smeared across the event horizon, or leaked out in subtle correlations? Increasingly, theorists believe that information is conserved, not because of classical determinism, but because it is a fundamental feature of reality. The holographic principle further deepens this idea. It suggests that all the information within a volume of space can be described by a theory that lives on the surface enclosing that volume. Like a hologram, where a two-dimensional film encodes a three-dimensional image, the universe may project its content from a boundary. In this view, space-time itself, with all its mass and motion, could emerge from a network of entangled information living on a cosmic screen. These ideas are not just speculative philosophy. They're borne out in string theory, the ADS, CFT correspondence, and studies of quantum entanglement entropy. When black holes are modeled as thermodynamic systems, their entropy measure of information is found to be proportional not to their volume, but to their surface area. This is not coincidence. It is a clue that information, not material, may be the real currency of the cosmos. In the context of quantum mechanics, the information universe implies that reality is observer-dependent. Until measured, systems exist in superpositions and clouds of possibility. Observation does not just reveal reality, it helps create it. Each measurement collapses a wave function, turning possibilities into facts bits into its. Even the arrow of time can be seen through the lens of information. The past is recorded, the future is uncertain. Entropy, often described as disorder, is more accurately the spread of information, the loss of specific knowledge about microstates as systems evolve. Time moves forward because information disperses. Philosophically, the information universe suggests a profound shift. If the cosmos is fundamentally informational, then our consciousness, our thoughts, decisions, dreams are not epiphenomena, but part of the informational structure. Minds process information. Reality does too. The gap between observer and observed begins to close. It challenges materialism without denying the material. It redefines the physical without abandoning the measurable. It proposes that reality is made not just of what is, but of what is knowable. That the deepest truths are not particles and forces, but patterns and relations, the software behind the appearance of matter. To explore the information universe is to see everything, stars, atoms, life, and thought as part of a cosmic computation. Not cold or mechanical, but dynamic, interactive, and alive with meaning. It is to look at the night sky and wonder not just what is out there, but what is being said. The quantum vacuum. We often imagine a vacuum as the absence of all things of pure void, a complete emptiness. Yet in quantum physics, the vacuum is anything but empty. It is a restless ocean of fluctuations, a theater of potential, teeming with virtual particles and ephemeral forces. The quantum vacuum is not the absence of reality, but a hidden foundation from which reality constantly emerges. At the heart of quantum field theory lies the notion that fields, not particles, are the true constituents of nature. Every type of particle electrons, quarks, photons, and excitation in a corresponding field that stretches across all of space. Even in the vacuum, when these fields are in their lowest energy state, they are never truly still. Quantum uncertainty ensures that they continue to fluctuate, generating temporary, virtual particles that flicker into and out of existence. These vacuum fluctuations are not merely theoretical. They have measurable effects. One of the most famous is the Casimir effect, in which two uncharged metal plates placed close together in a vacuum experience, a subtle force pulling them together. This attraction arises because the plates restrict the quantum fluctuations between them, creating a pressure imbalance with the surrounding vacuum. It is a tangible proof that the vacuum possesses structure and energy. Another consequence of the quantum vacuum is the Lamb-Shiftan observable shift in the energy levels of hydrogen atoms caused by the interaction of electrons with vacuum fluctuations. Even the stability of atoms, the colors of stars, and the properties of matter are subtly shaped by the energy that resides in this unseen sea. Perhaps the most significant role of the quantum vacuum lies in cosmology. The vacuum is not just a backdrop, it is dynamic and influential. The energy of the vacuum contributes to the cosmological constant, the term in Einstein's equations that determines how space expands. Observations of the accelerating universe suggest that vacuum energy is not zero, but small and positive, driving galaxies apart with increasing speed. This so-called dark energy may be a manifestation of the vacuum's latent power, though the discrepancy between theoretical predictions and observed values is immense, be a factor of 1,000,000, 12,000, and 10 circumflex, 120, 10,000, 120, the largest known mismatch in physics. This mystery remains unresolved, pointing to a gap in our understanding of how vacuum energy interacts with gravity and space-time. Some theories propose that different regions of the multiverse have different vacuum states, each with its own laws of physics. In this landscape of vacua, our universe is one bubble among many, stabilized in a local minimum of vacuum energy. If true, this would mean the vacuum is not just active, it is variable, creative, capable of birthing universes with distinct identities. The quantum vacuum also plays a role in particle creation in curved space-time. Near black holes, virtual pairs may become real lone particle falls in, while the other escapes, creating Hawking radiation. In the early universe, vacuum fluctuations stretched by inflation became the seeds of cosmic structure, tiny differences in density that eventually grew into galaxies, stars, and life. Philosophically, the quantum vacuum redefines our concept of nothingness. It is not absence, but potential, not silence, but a low hum of existence pulsing with probabilities. It reminds us that even where there appears to be nothing, there is the foundation of everything. To contemplate the vacuum is to consider that the universe is never truly still, never truly void. That reality is underpinned not by solid structures, but by subtle, ceaseless possibility. The vacuum is the breath beneath matter, the canvas beneath energy, the invisible background from which all things arise and to which all things, in time, may return. Multiverse theories. What if our universe is not the only one? What if the cosmos we observe is just one bubble in an infinite foam of realities, each governed by its own laws, histories, and possibilities? This is the idea of the multiverse, not a single universe, but a vast ensemble of them. It is not merely science fiction, but a serious consideration arising from multiple branches of physics and cosmology. The concept of the multiverse appears in several contexts. One of the most established is eternal inflation. According to this model, the rapid expansion that occurred shortly after the Big Bang did not end everywhere at once. While our universe stopped inflating and cooled into stars and galaxies, other regions continue to inflate and still do. This eternal process creates pocket universes, each emerging from its own Big Bang-like event, potentially with its own physical constants and laws. In this cosmic landscape, the multiverse becomes an endless mosaic of realities. Some might be like ours, with familiar particles and forces. Others might be unrecognizable universes, with no matter, no stars, or dimensions curled in unfamiliar ways. In some, gravity might be stronger, or time might flow differently. Each bubble is causally disconnected from the others, meaning we may never interact with them, but their existence might still influence what we see. Another version of the multiverse arises from quantum mechanics, specifically the many worlds interpretation. This interpretation suggests that every quantum decision, every time a particle could take one path or another, creates a branching of the universe. Each possible outcome happens, but in a different branch of reality. In this view, there are countless versions of you reading this script, each in a slightly different universe, shaped by the flow of quantum probabilities. String theory, too, contributes to multiverse thinking. Its complex mathematics permits an enormous number of possible solutions, each corresponding to a different way of compactifying extra dimensions and defining physical laws. The resulting string landscape offers potentially 1,050,010 circumflex, 510,500 or more distinct vacuum states, each a candidate for a separate universe. The question then becomes not why our universe has the laws it does, but why we observe this particular set of laws in this particular pocket. The multiverse provides a provocative answer to the fine-tuning problem. Instead of invoking design or coincidence, it suggests that we observe a universe compatible with life simply because only such universes can be observed by beings like us. This anthropic reasoning, while controversial, gains traction in a multiverse context is not that the universe is tuned for us, but that we happen to find ourselves in one where life is possible. Yet the multiverse raises deep challenges. It stretches the boundaries of testability. If other universes are forever beyond our reach, can their existence be considered scientific? Some argue that predictions of multiverse models still have observable consequences patterns in the cosmic microwave background or statistical signatures of inflation. Others suggest that the multiverse is more a framework than a falsifiable hypothesis. Philosophically, the multiverse is both humbling and unsettling. It dethrones our universe from a position of singular importance. It suggests that our entire cosmic history may be one thread in a vast, unknowable tapestry. It forces us to rethink uniqueness, significance, and the nature of reality. But it also expands our imagination. It invites us to consider that creation may be deeper and broader than we ever dreamed. That existence itself may be infinite in form and scope. That every possibility not only could happen, but does, somewhere in the ever-branching tree of being. To contemplate the multiverse is to peer into a hall of cosmic mirrors, where each reflection is a world, each variation a truth. It is to stand not at the edge of everything, but at the edge of one thing, with the rest receding into the boundless dark. Holographic principle. Imagine a three-dimensional world, vivid and real, full of space, matter, and movement. Now imagine that all of this, everything we see and feel, might be nothing more than a projection from a two-dimensional surface, like a hologram. This is not the premise of a science fiction novel, but a serious proposition in theoretical physics. The holographic principle, a radical idea that redefines the nature of reality and the structure of space itself. The holographic principle was born from the strange relationship between black holes and entropy. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole measure of its internal information does not scale with its volume, as one might expect, but with the area of its event horizon. This surprising result suggested that the information content of a black hole is encoded not within its interior, but on its surface. From this grew a deeper realization. Perhaps all of space-time, not just black holes, behaves this way. If a black hole's three-dimensional contents can be fully described by information on a two-dimensional surface, then maybe the universe itself is similarly encoded. The holographic principle, proposed formally by Gerard Hooft and Leonard Susskind, generalizes this concept, suggesting that the entire universe can be described by information inscribed on a lower dimensional boundary. One of the most compelling implementations of this idea is the ADS CFT correspondence, discovered by Juan Maldacena in 1997. In this duality, a gravitational theory in a higher dimensional space, anti-de Sitter space, is equivalent to a quantum field theory without gravity on its boundary. Every process in the bulk has a counterpart on the surface. The two descriptions are mathematically different, but physically identical. Though our universe is not anti-de Sitter space, the principle remains influential. It suggests that space-time, gravity, and even the laws of motion may emerge from a deeper layer of quantum information defined on the surface. In this view, the three-dimensional world we inhabit may be a projection of more fundamental data, a kind of cosmic code that generates geometry, matter, and time. This principle offers powerful tools for understanding quantum gravity. It provides a way to describe black holes without losing information, potentially resolving the black hole information paradox. It also hints that gravity itself may be emergent, not a fundamental force, but a statistical phenomenon arising from entanglement and quantum interactions on the boundary. The holographic principle touches not only theoretical physics, but our understanding of what it means to exist. If reality is a projection, then space may not be fundamental. Instead, it may arise from the entanglement structure of a deeper substratian invisible scaffolding from which all things emerge. Philosophically, this challenges our notions of substance and scale. We tend to think of larger dimensions as more real, more complete, but the holographic principle flips this intuition, suggesting that what we perceive as depth and distance may be illusions, born from the organization of information. That the inside of the universe may be, in a profound sense, encoded on its outside. It also reawakens ancient ideas that the world is shadow, projection, appearance. That reality is not what it seems, but a veil woven from the threads of consciousness, perception, and code. It aligns with the view that the universe is not a static stage, but an unfolding computation, a story written in symbols more fundamental than space and time. To explore the holographic principle is to wonder whether reality is surface or depth, illusion or essence. It is to see the cosmos not just as matter moving through space, but as information shimmering on a boundary waiting to be decoded, understood, and perhaps reimagined. Emergent space-time. What if space and time are not fundamental? What if they are not the fabric from which the universe is made, but patterns that emerge from something deeper, something more abstract, more mathematical, more informational? This is the idea of emergent space-time. That the continuum we experience, with its smooth distances and flowing durations, is not the base layer of reality, but a higher-level phenomenon arising from quantum interactions and informational networks. In this vision, space-time is like temperature in a gas. No single molecule has a temperature, but the collective behavior of countless molecules gives rise to this emergent property. In the same way, individual quantum events or entanglement links may not live in space, but when assembled in vast numbers, they create the illusion of space. Space becomes a map of relationships, not a backdrop for things to exist within. This idea gains traction from developments in quantum gravity, particularly in string theory, loop quantum gravity, and the ADS CFT correspondence. In ADS CFT, The geometry of a higher dimensional space is derived from the quantum state of a lower dimensional field theory. Entanglement, the correlation between parts of a system, is not just a feature of matter 8, seems to define geometry itself. Work by researchers like Mark van Ramsdonk and others has shown that when entanglement between parts of a quantum system is increased, the corresponding geometric space grows more connected. Reduce the entanglement, and space-time itself begins to fall apart. It's as if entanglement is the glue that holds space together. One metaphor for emergent space-time is the idea of a network or graph of nodes and links, where the connections define proximity. These links don't exist in space, they are space. Each connection represents a quantum relationship, and from the web of these connections, space is woven. Time, too, may emerge from causal structure, from the order in which events can influence one another. This perspective resolves some of the deepest paradoxes in physics. It helps address the black hole information problem, as information is no longer hidden inside a place, but spread across correlations on a boundary. It explains why gravity behaves thermodynamically because it emerges from the statistical behavior of underlying quantum systems. Emergent spacetime also has implications for cosmology. The Big Bang might not have occurred in space, but could be the moment when space itself emerged from a formless quantum state. Inflation, dark energy, and the expansion of the universe might reflect changes not in an existing volume, but in the patterns of entanglement that define volume in the first place. Philosophically, emergent spacetime invites us to rethink the nature of existence. If space and time are not fundamental, then neither is distance nor duration. The feeling of separation between objects or between moments may be a kind of illusion, a convenient interface rendered by deeper processes. We are not in space, we are made of space, in the same way waves are made of water. This reframing echoes ancient philosophical views. It resonates with the idea that the world is composed of relations, not things, that reality is not a set of objects, but a web of interactions. In this light, the universe becomes less like a stage and more like a song of harmony of relationships, a resonance of possibilities. To explore emergent spacetime is to peer beneath the veil of geometry and glimpse the quantum symphony beneath. It is to realize that what we call space may be the shape of information, and what we call time may be the rhythm of its change. That the cosmos, in all its vastness, is not built from emptiness and matter but from meaning, connection, and unfolding form. Quantum loop gravity. In the quiet heart of theoretical physics, where equations whisper of origins and boundaries blur between certainty and wonder, a subtle and elegant theory takes shape. Here, in the ongoing quest to reconcile the two great frameworks of modern science, Einstein's general relativity and quantum mechanics, there exists a vision that neither stretches the universe across vibrating strings nor embeds it within unreachable dimensions. Instead, it rebuilds the cosmos from loops, not of thread or twine, but of geometry itself, infinitesimal interlacing loops that weave together the very scaffolding of space and time. This is the world of loop quantum gravity, LQG, a theory that proposes a radical shift in how we understand the universe's fabric. It suggests that space is not continuous and smooth as our eyes perceive it, but granular, textured, and fundamentally discrete. Just as matter is composed of atoms, space according to LQG is made of indivisible quanta, elemental units of geometry, minuscule and interwoven in a cosmic lattice. And time, long treated as a flowing river or a ticking clock, is revealed here not as an absolute rhythm, but as a rhythm emerging from change, from the choreography of these loops. At its foundation, loop quantum gravity embraces a simple yet revolutionary premise. Space is quantized. Beneath the scale of everyday experience, at lengths on the order of the Planck scale are roughly 10⁻³ circumflex, 35 10⁻35 meter space-time ceases to behave like a smooth continuum. Instead, it becomes pixelated, not in appearance, but in structure. The vacuum, far from being empty, is a dense forest of loop-steny circuits of gravitational flux, twisting and linking in a silent, invisible network. These loops assemble into what are known as spin networks. These are not spatial diagrams in the ordinary sense, but mathematical objects graphs whose edges carry quantum numbers corresponding to areas and whose nodes represent volumes. Each link defines a quantum of area. Each node defines a quantum of volume. The geometry of space is no longer a background, given it is a living, breathing participant in the drama of existence. The spin network pulses and transforms, not continuously but through quantum jumps, evolving through a structure known as a spin foam, which traces how spin networks evolve through time in a fundamentally timeless theory. Loop quantum gravity discards the notion of a fixed space-time stage. It is background independent, a phrase rich with philosophical weight. Traditional physics often assumes a pre-existing canvas upon which matter and energy paint their patterns. But LQG says there is no such canvas. Instead, the canvas itself is woven from the threads of interaction. Geometry is not static, it is relational. The distance between 2 points is not absolute, but depends on the web of quantum correlations. Time, likewise, does not flow independently. It arises from sequences of change, from the comparison of configurations within the network. In a universe described by LQG, clocks don't tick uniformly across space. Rather, time is local, emergent, subjective in expression of comparison, not of absolutes. One of LQG's most profound contributions is its approach to the problem of singularities. In classical general relativity, certain solutions to Einstein's equations, such as those describing the Big Bang or the center of black holes, lead to singularities, points where curvature becomes infinite and known physics breaks down. These singularities signal a failure, a place where our understanding falters. But in loop quantum gravity, the discrete nature of space-time prevents such infinities from forming. The theory replaces the singular beginning of the universe with a quantum bouncer scenario where a prior contracting phase of the cosmos transitions into the expanding universe we observe today. Likewise, inside black holes, where general relativity predicts an inevitable gravitational collapse into a point of infinite density, LQG suggests that quantum geometry steps in to resolve the singularity. The infinite is replaced with a quantum bridge, a region of extremely curved but finite space. This opens the tantalizing possibility that information falling into a black hole is not lost, but transformed, preserved in the structure of the loops, and perhaps re-emerging elsewhere. In this vision, the black hole information paradox begins to dissolve, and with it, a long-standing fracture between quantum theory and gravity begins to heal. Unlike string theory, which attempts to unify all known forces including electromagnetism and the nuclear forces under a single theoretical umbrella, LQG is more focused in scope. It does not attempt to unify everything at once, but instead dedicates its attention to understanding gravity at the quantum level. And in doing so, it retains mathematical rigor, elegance, and internal consistency without requiring the addition of extraspatial dimensions or the introduction of entities that cannot yet be observed. This humility of scope does not diminish its ambition. Rather, it strengthens its foundation. LQG does not assume a structure and then feel it builds the structure from first principles. And while experimental confirmation remains one of its greatest challenges, given the minuscule scales involved, there is growing optimism that LQG might leave subtle fingerprints on the universe. Some researchers suggest that tiny traces of quantum geometry might be embedded in the cosmic microwave background, or in the radiation patterns emitted from black holes or neutron stars. Others believe that future gravitational wave observatories could detect the echoes of quantum spacetime in their data. Philosophically, loop quantum gravity speaks to a deep and resonant idea that reality is fundamentally relational. It challenges the classical view of the universe as a collection of objects moving through an inert void. Instead, it offers a vision of the cosmos as a network of interactions, where location is defined by relation and where being is an emergent property of becoming. This echoes the insights of ancient metaphysical traditions, that the world is made not of things, but of patterns. That existence is not substance, but resonance. That time is not a universal river, but a local tide. That reality, at its deepest level, is composed not of solid bricks, but of shifting loops, each one a quantum breath in the lungs of space. To contemplate loop quantum gravity is to reimagine the very texture of being. It is to abandon the image of space as a void and replace it with a lattice shimmering, dynamic, and alive with geometry. It is to imagine the cosmos not as a static cathedral, but as a woven song, each loop a note, each foam a measure. The music of the universe is not sung in sound, but in structure, not played on strings, but traced in loops. And in the end, what emerges is a vision of reality, not as fixed, but as unfolding. Not as absolute, but as relational. Not as a place we are in, but as a process we are part of. The universe is not merely what surrounds you, it is what we are made of, down to the smallest loop, the quietest rhythm, the softest fold in space-time. Loop quantum gravity invites us to look not just outward into the cosmos, but inward into the architecture of understanding. It calls us to see with new eyes, not the eye that seeks objects, but the one that perceives connections. In that seeing, we find something rare, a universe not of solitude, but of symphony, not of fragments, but of entangled wholeness. Time as an emergent phenomenon. Timur, most intimate experience. Our ever-flowing companion is perhaps not what it seems. We live within its current, guided by its rhythm. We feel it in the beat of a heart, in the ticking of a clock, in the blossoming and withering of life. It defines the arc of our stories, shapes the meaning of our memories, and grants urgency to our actions. Yet, in the silent, impersonal language of physics, time often plays a more elusive role. The equations that govern particles, fields, and forces do not always require it. Some work equally well in both directions, others omit it altogether. This realization is not merely academic, it strikes at the very foundation of what we believe reality to be. In the deep structure of theoretical physics, particularly in the attempt to merge general relativity with quantum mechanics, a radical possibility arises that time is not fundamental, that it does not exist independently, flowing like a river regardless of what occupies it. Rather, that time is emergent, a consequence of relationships, a shadow cast by change. To see how far we've come in thinking about time, we must begin with Newton. In classical mechanics, time was absolute, a uniform, unchanging background against which events unfolded. It was as real and as rigid as space itself, a grand clock ticking away regardless of whether anything was happening. In Newton's universe, every event could be marked along a single timeline, shared by all observers, true everywhere and always. But Einstein changed this view forever. With the advent of special relativity, time became relative, no longer universal, but dependent on speed. Two observers moving at different velocities would not agree on the duration of an event. And with general relativity, time became elastic, bending under the influence of gravity. Massive bodies could slow it, warp it, even trap it within the event horizon of a black hole. Time was no longer an impartial stage. It had become a player in the cosmic play. Still, even within relativity, time remained part of the fabric of space-time, a four-dimensional continuum, where every event had a specific coordinate. But in the quantum realm, this continuity begins to fracture. In quantum mechanics, time is treated differently than space. It is a parameter, not an operator. This asymmetry has long puzzled physicists, and when we attempt to combine quantum theory with general relativity into a coherent framework of quantum gravity, time often vanishes entirely. Nowhere is this more striking than in the Wheeler-DeWitt equation, a central equation in canonical quantum gravity. This equation describes the quantum state of the entire universe. Yet, astonishingly, it contains no time variable. The wave function it describes, often referred to as the wave function of the universe, is timeless. It does not evolve. It simply is. This led to what some have called the problem of time. If the most fundamental description of the cosmos contains no time, how do we reconcile this with our experience of its steady passage? How do we explain the unfolding of events, the sense of before and after, the forward arrow that seems so evident in everyday life? One proposed resolution is that time is not fundamental but emergent. That is, it arises only within subsystems of the universe, when one part is used as a reference to track changes in another. In this relational view, time is not a thing in itself, but a bookkeeping device for relationships. When systems interact and evolve relative to each other, a notion of time emerges. One part can be treated as a clock, and its changing state gives meaning to the evolution of the rest. Consider a closed quantum system. On its own, without an external clock, it does not know time. But if one component of the system is chosen as a reference, say, a particular particle or degree of freedom, then its change can be used to describe the evolution of the other parts. In this way, time is not an absolute dimension, but a relational phenomenon, dependent on the choice of observer and system. This idea is further illuminated by the role of entropy in thermodynamics. The arrow of time, the fact that we remember the past but not the future, that eggs break but don't unbreak, that systems move from order to disorder arises from the second law of thermodynamics. Entropy, the measure of disorder or information loss, always increases in a closed system. This gives time a direction, an asymmetry. But entropy itself is a statistical measure, dependent on our coarse-grained ignorance of microscopic details. It is not a law written in stone, but a probabilistic tendency. This suggests that the arrow of time, too, may be an emergent feature, not an inherent property of the universe, but a consequence of how we observe and interact with it. Time moves forward not because the universe demands it, but because our limited perspective constructs it that way. Decoherence adds another layer to this emergence. In quantum systems, superpositions of multiple states can exist until the system interacts with its environment. This process, known as decoherence, effectively collapses the superposition into a definite outcome, giving rise to classical behavior. Some physicists argue that the perception of sequential events of a flowing time emerges from the cumulative effects of decoherence. The transition from quantum indeterminacy to classical definiteness is not just the origin of measurement, but of history itself. In theories of quantum gravity, time is notably absent or redefined. In loop quantum gravity, the universe is described not by a background spacetime, but by networks of quantum relationships. Events do not occur in time, rather. They constitute the fabric from which time arises. In causal set theory, spacetime is built from discrete elements linked by cause and effect relations. Time is not a smooth dimension, but a hierarchy of events. In holographic models, such as the AS, CFT correspondence, even spacetime, including time, can be derived from lower dimensional quantum theories. In these models, time does not exist on the boundary theory. Instead, it emerges in the bulk as a geometric consequence of entanglement and quantum complexity. This brings us to the profound philosophical implication. If time is emergent, then so is the past. The future is not a predetermined path we march toward, but a construction that emerges from the configuration of present relationships. Memory, expectation, identity all are layered into this emergent 141 to 15, 144 to 30 temporal fabric. We do not drift helplessly down a river of time, we participate in its creation. Our experience of time is woven from the changes we observe, the patterns we construct, the narratives we assemble. This challenges the deeply ingrained metaphor of time as a container. Instead, it invites us to view time as a lens, shaped by our interactions with the universe. It invites us to see the cosmos not as something unfolding in time, but as something from which time itself unfolds. To contemplate time as emergent is to turn inward toward a deeper understanding of existence. It is to recognize that the ticking clock, the setting sun, the aging face in the mirror, these are not illusions, but interpretations. They are the shadows cast by deeper realities. In that awareness, we find freedom. Time becomes not the master of being, but the echo of being. Not the dictator of destiny, but the whisper of change. Ultimately, the idea that time is emergent invites not despair, but awe. It reminds us that the universe is more subtle than our instincts suggest, that beneath the smooth flow of days and nights lies a network of relations, an intricate tapestry of quantum logic and thermodynamic arrows. It tells us that we are not passive victims of time's passage, but co-authors of its meaning. Final reflection, the silent architecture. At the end of this journey through the most profound and perplexing ideas in physics and philosophy, we find ourselves pausing not at a destination, but at a quiet threshold, a moment suspended in reflection. For in exploring the nature of reality from the glimmering surface of space-time to the hidden algorithms that may underpin it, we have brushed against something greater than explanation. We have sensed, perhaps for the first time, the contours of a silent architecture. What is this architecture? It is not built of matter in the traditional sense, not carved from atoms or quanta. Rather, it is shaped by principleless symmetries, transformations, abstract structures that guide how existence expresses itself. It is a scaffold not of stone, but of ideas, invisible, indivisible, and everywhere. In our journey, we've crossed many conceptual thresholds. We began with familiar terrain, time and space, gravity and energy. But soon we ventured into quantum realms, where particles are waves and certainty dissolves into probability. We trace the tremble of time crystals, the firewalls of black holes, the shimmering hints of holographic screens. Each idea, a window, each theory, a key. Each paradox, a reminder that reality is stranger and more beautiful than our everyday senses can perceive. At every stage, the theme reemerges, that what we see is not all there is. The universe, it seems, wears masks. The face of matter hides the dance of fields. The continuity of time conceals its granular possibilities. The surface of things conceals interconnections that span great distances and deeper meanings. Even space, that which feels so solid beneath our feet, is not immutable. We've learned that space might emerge from entanglement, from webs of relationships, rather than extension. That distance may be illusion. That place is not absolute. Instead, it is coded, relational, woven from threads of quantum interaction. If so, then what of time? Time, that quiet river we all float upon, proves even more elusive. In the deepest equations of the universe, time often disappears. It is not fundamental. Instead, time is born from change, from the evolution of one system relative to another. It is not the frame but the process. It is not the engine but the rhythm. And what does this mean for us, for the conscious beings trying to make sense of all this? It means we are not merely observers, not passive recorders of cosmic fact. We are participatory nodes in the unfolding of the cosmos. The observer effect in quantum mechanics is not a metaphor, it is a signpost pointing to a deeper truth, that reality, at its root, is interactive, that knowledge and being are not separable. That consciousness, however mysterious, is not foreign to the universe. It is one of its most exquisite expressions. We have spoken of black holes and bouncing cosmologies, of wormholes and quantum foam. But beneath it all lies a single question. Whispered through all these ideas, what is real? To ask that question is to confront not just the limits of our understanding, but the nature of understanding itself. Perhaps reality is not a thing, but a relationship. Perhaps truth is not found in static definitions, but in evolving frameworks. Perhaps existence is not substance, but song a harmonic structure that reveals itself only in motion, in change, in becoming. And what of beauty? So much of what we've explored carries an undeniable aesthetica sense of balance, elegance, and unexpected unity. Equations that bind electromagnetism to motion, symmetries that link forces to particles, geometries that turn information into form. This beauty is not incidental. It is a clue, a signal that the universe is not random chaos, but an artwork and unfolding poem written in the language of structure and chance. We must also acknowledge humility. For all our theories, models, and mental maps, we remain beings bound to limited perception. We peer through instruments, we simulate, we measure, and record. But what we know is only a fraction of what is. The dark matter that binds galaxies, the dark energy that accelerates space, the fundamental nature of consciousness itself, these remain veiled. We are stargazers with lanterns, catching only glimmers of a vast and layered cosmos. Yet this humility is not defeat. It is reverence. It is the recognition that wonder is not the absence of knowledge, it is its origin. It is the awareness that mystery is not the enemy of science, but its pulse. There is something sacred in this inquiry, not in a religious sense, but in the sense of sacredness that comes from depth, from awe, from silence filled with potential. The universe is not a machine grinding without care. It is not indifferent. It is patterned, responsive, strange, and precise. And we, brief sparks of awareness, are part of it, not above it, not below it, but within it. And so we return to the silence. The silent architecture is not just in the stars. It is in the logic of primes, the elegance of pi, the spiral of a galaxy mirrored in the spiral of a fern. It is in the rhythm of breath, the recurrence of seasons, the resilience of systems. It is in the pause between thoughts, the spaces between words. It is in what we do not yet know and may never fully know. Some may ask, is this journey of discovery worth it if the answers always lie just beyond reach? To that we say, yes, because the search itself is illumination, because to question is to awaken, because even if we never reach the final theory, We are participating in the greatest story ever told, the story of a universe awakening to itself. In every theory, we embed our curiosity. In every paradox, we find our limits. In every elegant solution, we touch a fragment of the whole. So we keep going, not to end the mystery, but to deepen it, not to possess the truth, but to stand in its presence, not to conquer the cosmos, but to harmonize with its music. As we close this reflection, we do not say goodbye. We say, begin again, ask anew, dream further. For the silent architecture is still building itself, and we watchers, thinkers, makers of meaning are part of its construction. Let us go forward not with certainty, but with wonder. Not with final answers, but with enduring questions. Not with fear of the unknown, but with the joy of discovery. And when we next look up at the stars or down into the smallest depths of matter, let us remember, we are looking not just outward, but inward, into the code of reality, into the self-revealing structure that holds both galaxies and grace. In the end, perhaps, the universe is not only physicalite, is poetic, not only factualite is luminous, not only what is but what becomes,